send someone regardless.
Oh, okay, cool.
Why won't it go to it? Yeah, let's send
Oh,
someone
cool.
regardless.
It'll be in the middle of the first keynote because that's or would you prefer like stay entire thing?
So the door is there. I think when the keynote goes to questions, you can name.
Oh, okay.
Just tell me that keynote has gone to questions. Just add me as a keynote.
Oh, in that case, I'll just stay here for the entire thing. Since it'll be halfway through the talk, I want to go to like
Which one is it?
it's the PO and the
Yeah.
but it's fine. I've seen that talk before, so don't worry about it.
Are you sure?
Yeah, it's fine.
Is there any other thoughts you want to?
They're always the afternoon, so it's
Okay, all of that.
yeah. So don't worry about it.
Okay.
Yeah. One thing I was wondering
Yeah.
is, do we need a USB and HDMI to USB-C?
No, they're supposed to bring their own. They're supposed to bring their own, but there's like really additional numbers. Yeah.
Okay. And I should do the handheld session chair.
Yeah, one to the second chair, one to the volunteer.
Okay.
And
no lapel lines, but that's from
oh, there's no lapel.
There's no lapel. That's what I was told.
Yeah, that's fine. Yeah. And then you can ensure that there's no phonic, and if the speaker wants to walk around, they should use it.
Oh, okay,
And
cool.
we have a clicker somewhere.
Oh,
Might be on the podium. No, okay, that's fine. We just don't have a clicker.
okay.
Yeah. So just use the lectern for any speakers.
Okay, sounds good. Okay. Hi, I'll be the student volunteer managing the projector and the live stream during the session this morning. Here is a microphone for you. And then there'll be another volunteer with this microphone for questions.
Yeah, okay, so I have to move on that.
Yes.
Hi, are you the chair for the session?
Yes.
We have a student volunteer for you, but they will be arriving.
Welcome everybody. My name is Meng Wang and I'm one of the program chairs of this workshop. Another program chair is of course Gabby Keller, who has worked with me to organize this year's program. And also I want to mention Fritz also helped us in organizing the last session, which is kind of special because for this year, different from other years, that we are actually celebrating 30 years of PEPM. Right. So to commemorate on that occasion, we are organizing a special session that toward the end of the day, you will see it on the program, and that will be very interesting and exciting. Make sure that you stay for that. Right. And before that, for the whole day, we have exciting talks contributed by the authors that are sitting among us. And there will be just a few kind of logistic things that organizers asked me to tell everybody. The coffee and tea will be upstairs in the library or reading room. And the terrace, I don't know where it is, but the terrace is supposed to have a very good view of London, so make sure that you enjoy it. And the Wi-Fi password is upstairs by the registration desk. And there will be lunch. I don't know where it is, but just follow everybody else. Okay, so yes, so that's the beginning of the first session. And I would like to welcome our keynote speaker, Alexandro Rosso. Alexandro and I went a long way back. We were colleagues back at Chalmers University. I've taught technology, but I'm still going to look at the bio he has provided because there's so many great achievements that I fear that I may forget some. Have a rest. Yes, so Alejandro is a professor at Chalmers University at Technology, and I would like to add that his career basically rocketed. He finished his PhD ahead of the time, then very quickly move on to assistant professor, then very quickly to be promoted to associate professor and professor. That was many years ago. Then he has worked on the intersection of functional programming, security, privacy, and systems. Right? So for us who has worked in the intersection of areas, it is actually a very tricky place to navigate. Right? You may enjoy great success, you may fall in the track. Nobody likes you, nobody publish a paper. But Alexandro somehow managed to be a great success. He is a recognized figure in programming languages and also in security. His research ranged from fundamental aspects of security to practical ones. And he has a close connection with Stanford, which is also kind of prestigious. Just to mention, he received the most influential paper award at ISFP 2022 for his library, I believe, for security, language-based security in Haskell. And as well, distinguished paper award at POPL 2019. Just add to that list of already remarkable achievements as an academic, he recently has become a CEO of a startup called POPL'24. It is a startup providing differential privacy solutions in Haskell. Right. So I believe that's going to be his topic today, that we'll be talking about from theory to practice, crafting differential privacy systems with Haskell. And I was told that there will also be a connection to a partial evaluation, very fitting for this workshop. Thank you.
Thanks, man. Thanks a lot. Thanks a lot for the introduction. Yeah, I can tell you one connection. I'm super honored to be here. So let me tell you one connection I read with PEPM. My first ever paper that I submit to ever computer science conference was to PEPM. Like 19 years ago. Yeah. Let me see. All right, yes. Today, essentially, I'm going to take you in a journey that I've been taking in the last 3 years, where I've been working on data privacy topics from a PL perspective, and as well a little bit on the system perspective. We will do some live coding. You will learn something about differential privacy, and then I will give you some reflection about, trying to take something like this into practice, in case you are motivated to do the same with your research. All right, so let me start with some introduction. So today it's all about data. Like never before, companies and governments are collecting data, and they want to mine that data to learn how customers or citizens are using services, okay? And you want to learn about trends in population, what you call as data insights. And you want that data to be shared among your own partners or among different governmental entities. And the main challenge is how we do that in a way that by sharing the data and someone observing the data, we do not reveal who is in the data set. Okay? So, because it could be like, it could be like, people sick with certain disease. You share analytics. You don't want people to guess by looking at analytics who is sick. So this is the main problem that we have today, data sharing and privacy. How do we share insights about data sets while preserving privacy? This is a hard problem. And industry is screaming for this. But not take my word for that. This is the Swedish IMI, the Swedish Agency for Regulating GDPR. GDPR is a regulation in Europe that tells you how to handle personal data. And they got a mandate from the government to say, please investigate what is the most roadblock that we have to make Sweden the data-driven nation, the leader data-driven nation in Europe. And it's like this, so I don't expect you to understand that, but it says more or less that data sharing is without reason the most difficult part. Data sharing while preserving the confidentiality of the information, like only the parties authorized to see it will see it, but as well to preserving the privacy of the individuals. Okay? But there are many ways to share data and privacy. There are different scenarios. So let me set up the one that we're going to use for this talk. In this talk, we're going to consider someone called data curator. Data curator is someone that owns a data set and cares a lot about privacy. Imagine you are the CIO, the Chief Information Officer in a company, and you have your customer database. You care about the privacy of that, okay? Then on the other hand, you will have the data analyst who wants to extract information from the data sets, okay, in the form of analytics. So we need a technology, we need a technique that enables the data curator to share those insights while preserving the privacy of the individuals. So data curator cares about privacy, not so much about the analytics, and analysts care about getting insights, not so much about privacy. We are going to put in these black and white terms, okay? All right, this talk is going to be based in some papers that I've been working in the last 3 years, plus some unpublished work, okay? So what I'm going to present you here is a system called Dipela. I'm describing, I can explain what it means. Usually I cannot explain, so I will do it. It means differential privacy in Haskell with accuracy. And you will understand that what it means in the end of the talk. And the idea is like a data analyst in a DSL writes some Haskell code to do a query on the data set, and then it gets analytics back. And all of that while having certain privacy guarantees, okay? All right, so to preserve privacy always comes to a cost. Protecting privacy is never for free, okay? And the techniques that protect privacy when you are releasing information, like we are allowing people learn from our data set, the price to pay is the accuracy of the analytics. How accurate is the data? The more privacy protection you have, the less accurate it will be. The less accurate it is, the less privacy you have, okay? So in this talk, I'm going to present you differential privacy, which is a privacy definition that has some mathematical foundations that allow you to reason about this trade-off between privacy and accuracy, okay? How much privacy we have and how accurate or useful are the analytics I will get. Okay, so now I will go through a background in differential privacy, very quick background. So bear with me. So, as I said before, differential privacy is a definition. It's from 2006 from some theoretical computer scientists. And the definition entails to consider data sets, right? And data set here, we're going to consider that a row in the data set has information about one individual, and that's it. So every row has information about individuals. Then the definition considers adjacent data sets. Those are data sets. If you see D1, the difference between D1 and D2 is like you remove one row. Okay? You remove one row or you add one row. You remove one individual or you insert one individual. The definition also considers a randomized query, Q tilde. It's randomized, means like every time that you run the query on the data set, it's likely to return different results. Okay? And the definition relates the probabilities to run the query in D1 or in D2. Right? It says, if you run the query in D1 and you observe something, that's what it says belongs to S, that's something. It's similar to running the same query in D2 and observe the same thing, module some factor e to the power of epsilon. Okay? So it's telling you that running the query in one data set or in another one where you have removed one individual is almost the same in this notion. Which means like it's hard to see where the result comes from, if it comes from D1 or from D2. So in that way, you protect the presence or the absence of an individual. Okay? And this is true for all individuals that you choose to remove from the data set. Let me show you more graphically here. So you have, Q tilde applied to D1, now it's a distribution. Q tilde applied to D2, it's another distribution. And you can see here that the probability to observe 0 in D1 or in D2 is not the same, but there is a gap there. And that gap is regulated by epsilon, which is called the privacy parameter. The smaller the epsilon, the distribution will get closer and closer. The harder it is to distinguish if the result comes from D1 or D2. The bigger the epsilon, the more far apart the distribution is going to be, the easiest is to distinguish if it comes from D1 or D2. It doesn't mean that it's going to be easier, but it's easier. Okay? Right, and this definition gives origin to some composition principles that are very useful for writing or building systems. One is called sequential composition principle, which is the most simple one, that says, if you have a randomized query that is epsilon 1 differentially private, satisfies the definition, and you have another one that is epsilon 2 differentially private, and you want to run them both as a unit, as a one, it's like you put a semicolon in between. Sorry for using a semicolon in a functional setting, but yeah. So the whole block is epsilon 1 plus epsilon 2 differentially private. Okay? So if you have differentially private queries, you run them in a sequential way, I still have a differentially private query with epsilon 1 plus epsilon 2 as a privacy parameter. Okay? And then you have the other one, which is called the parallel composition principle, which says if you have two queries, again, differentially private ones, but you run them on different part of the data set that is joined, if you run them both and obtain the result, the whole block is going to be differentially private, but where the epsilon is the maximum between E1 and E2. Okay? So don't worry so much about the parallel composition. This is the one that we're going to use in the talk. But just for you to get an intuition, like this definition has some composition properties that enable you to build systems. Right, and we're going to use the sequential composition principle to define what is called a privacy budget. The data curator, remember, is the one arguing for privacy, and he set up a privacy budget and epsilon, right? Let's say 2. You can see that epsilon like a bag of coins, right? And you want that all the queries that you're going to do to the data sets will never be more than 2 epsilon differentially private. Okay? So then you distribute the coins against to the different analysts. So the first analyst, let's assume, receives 1, and he does a query. When you do a query, you need to pay. You need to consume the coins, right? Once you consume it, they get burned, right? And for example, 1, you burn it, you get some analytics results, and then the rest that also receive tokens, they can pay for that, and get analytics back. Since you have epsilon 2 as a privacy budget, whatever you do, the composition of all those analytics will be differentially private, but never more than 2 epsilon differentially private, right? Once you exhausted the budget, right? When it disappears. You cannot query the data set anymore. Okay? Right, so how do we build these randomized queries? And I'm going to show you one simple way to do it. So then, you have the whole picture, how this works. Imagine you have the query that say, we need to count how many employees have salary bigger than 60K, right? The way that we're going to create this randomized query is taking the original query, the privacy parameter, and we're going to synthesize the Q tilde. And we're going to do it in the following way. We just add noise to the original result of the query. But that noise needs to come from a special distribution, which is the Laplace distribution centered in 0, with an scale of sensitivity over epsilon. I will tell you what that means, but the scale regulates how pointy the Laplace distribution. The Laplace distribution is like this. It regulates how pointy it will be, okay, or how flat it will be. You see the privacy parameter there, epsilon there, and the sensitivity, I'm going to be very informal, but the sensitivity is like, if I change the data set, how much the output will change. If I remove one person, I run the query, and now I remove one person, and I run the same query, how much that query has changed? Because here we are counting, if I remove one person, the output will change almost once. If I remove 2 people, the count will change almost 2, right? So the difference between what I change in the input and when I change what the output changes is a factor of 1. So we say that the sensitivity is 1 for counting. All right, the good thing that all of this, you see a lot of heavy math, but some math. And we are going to package all of that and give you a DSL where you can write queries which are differentially private and support this notion of privacy budget. Okay? And you are the data analyst, and I'm going to give you my DSL, right, to play with it. So the first thing you need to do is to learn about 3 abstract data types: datasets, value, and query. Dataset means it's a dataset. It has 2 type parameters. We skip the first so far. We focus on the second one. It's the type of the row in the dataset. Then we have values, which are values that has been generated with the Laplace mechanism. So values where noise has been injected. And then we have queries, which has a monad structure. It means it's a collection of instructions. In the PEPL we have 2 kinds of instructions. One is called transformations. It takes a dataset and returns a dataset. You can filter it. You can map it a function over a row. You can union, intersect, group by, and so on. So the PEPL supports to do those transformations and any combination of it. And then the second kind of instruction we will have in queries are measurements. This is when we learn from the data. And that's when we need to inject the noise, right? Because those are the insights that we're going to share or publish. The measurement is counting, like the query that you saw before. We are counting certain events, the size of a data set. We sum a column, or we do an average, okay? And the PEPL supports you take all these results and do any linear combination of them, okay? All right, are you ready to play with it? All right, let's take one transformation and one measurement and then do something with that, okay? All right, so this is one transformation called dp_where. It's a filter. You give me a Boolean function, you give me a data set, and I give you the query that filters that data set. Let's take the measurement of counting. You give me an epsilon, how much you are going to pay for the query, the data set, and I return you a noisy value, the result produced by the Laplace mechanism, okay? All right, so this is risky, so we see how this goes, but let's do it. All right, here what I'm going to take is a data set called adult, which is a famous, oh yeah, sorry. Yeah. Let me see if I can. Sorry about that. I'm going to mirror the displays, and then I keep it like that. Let's see. Yeah, now you see it? What? Sorry, give me a second. Yeah. Sorry, I didn't realize about this. Okay, keep changes. Now you should see it. Now you're with me? Yeah. So I have a adult data set that is about information about the population, right? So it has an age, the work class, education, the occupation, the relationship. And you see that there are like 33,000 rows, okay? So let's model that into Haskell. So here I have a file that is going to use dpella. And for every column in the data set, I assign a type. Columns in data set are known as attributes. So for every attribute, I have a type. And then the type of the row is just a record. Okay, that you see here. Age, work class, blah. Okay? So now let's build a simple query that I want to know how many females are in the data set. Okay? I create a function that you need to provide the sex that you're going to filter upon. In this case, it's going to be female, but let's keep it general. Epsilon, how much you're going to pay for the query. The data set, which is the data set adult. That's why the type of the data set has the type from adult. You want to make it bigger? Yes. Yeah, sorry. Yeah, let's move this out. Is that okay? All right, that's better? Yeah, thanks. All right, so here what we're going to do is like, we're going to use dpware. So we say, okay, I need to filter the data set. Some function, and then the data set I'm filtering is ds. So I say, well, give me the row, give me the input that you want to be interested in, the sex you are interested in, right, S. And then I say, well, I extract from the record the sex of that person. All right? And now what I do is a dp count. I pay epsilon in ds prime. Okay? The query is ready. Now what we can do with dpella, we can check, is this query using epsilon? How much budget is using? How much coin is burning? Right? So I can say, well, let's, I'm going to call this function, call budget. Give me a query, and I give you how much budget is there. Okay? So, and I say, well, let's do the budget of simple count. Female, epsilon, let's say 1. And I need the data set. But I don't have the data. The good thing is that all the analytics done by dpella are data independent. So you don't need the actual content of the data set. You need a symbolic data set. So here I put symbolic data set, and I will explain you what this @1 means in a second. Okay? So if you see, I apply all the parameters of simple count, and I have a query, I evaluate, and it says 1. Right? But now we can do like this. We can say, well, maybe the programmer did a mistake and took the epsilon, and I thought, okay, I can use it 10 times. Right? And I call again. Now it says 10. Okay? And you can see here that these are all Haskell expressions. Okay? Right. Now we can run the query actually. Let's go back to 1. Sorry, how it was before. Now we can run the query, and the query will load all the data from the adult data sets. And this is we are going to use dp-eval. And let me show you the type of dp-eval. Give me a function that takes a data set, ignore the 1, and returns a query. Give me the content of the data set, and the epsilon. This epsilon is the privacy budget. And then I will run it. So dp-eval is used to set up the privacy budget of the query. So here we can see here, like, I want to run this with we say epsilon 1, and the budget is 1. So that should work. And then we say, okay, there are around 10,000 females in the data set. That number has noise injected. How accurate is that number? We will see in a second, right? But we can see here just like if we try to use more budget, that's what is allowed. It will say not enough budget. One invariant that you should think when choosing how much to pay for a query, the more you pay, the more accurate it will be. The less you pay, the less accurate it will be. Okay? So here, if I pay just very little, we see that the value is 3,000. If I run it again, you see there is a lot of noise being injected. Okay? We will see how to reason about the accuracy in a second. Okay, great. All right. So now, for the sake of completeness, let me tell you about the parameter S here. Yeah, we have seen so far that when we do all this reasoning about how to calibrate the noise, we say we need to understand the sensitivity of the measurement we are doing. If it's accounting is 1, because if I add 1 person or remove it, the result changes at most by 1, because I'm counting. We say sensitivity is 1, great, we inject the noise, everything perfect. But there are situations where if you do some transformation before, this relation between how much you change and how much impact your output doesn't hold. Let me give you an example. For some reason, you take the table of this adult table and you separate between European and Latin Americans, and then you just join them. Right? Very inefficient, but some way to do transformations. If I add or remove 1 person here, and the person has double citizenship, it will go in both tables. When I do the union, I will have that record repeated. So now, I add or remove 1 person, but the count will be changed by 2. Okay? So that's what this S parameter is about. It's called the stability of the table, which says when you do a transformation, how much removing or adding 1 person gets magnified in the resulting table. So here, we are filtering, the stability is 1, because if I add or remove 1, when I filter, I will see that once, at most once, right? Or it's not there. So, but in the union, it's just addition of the 2 stabilities, right? We keep track of that, and we adjust the noise so that now it is differentially private. Now it's taken into account that transformation can magnify the presence or absence of a person plus the sensitivity of the function. So in this way to do things is differentially private. Okay? All right. So and here you can see the rest of the transformations, and we play with where and union, and you can see union there, and how it's using the type level numbers to keep track of the stability. Right? And you have DP count here, sum, averages, and maximum. Right? The rest of the API, and that's it. There is no more. Okay. All right. So let me talk about accuracy. How accurate are our results, and how can we reason about that? This is something that usually lacks in differentially private tools, but in the PEPL we decided to embrace it from the beginning. Right? Accuracy is as important as privacy. Right. So we need to define accuracy. How do we do that? Well, we need to reason about the actual result of the query. Remember, we have a query Q and a randomized version of that called Q tilde, where we inject noise from the Laplace distribution. If you run the query in D, it gives you 1 point. That's a real result. If you run the query Q tilde, it's a distribution. So we need to reason about how far the points in the distribution are from this real point. And the way that we're going to do that is by using confidence intervals, and I'll give you the definition. It's like this. You're going to reason about the distance between a point in the distribution Q tilde and the real point. The important thing here to notice are 2 parameters, alpha and beta. Alpha is the error, and beta is the confidence parameter. Okay? And you need to think it a little bit in the dual way. You say, like, if beta is 0.05, it means that 90% of the time, the distance between a point in the distribution and the real point is bounded by alpha. So alpha is error with 95% of confidence. Okay? All right. So we continue with this. And hopefully, yeah, excellent. That's everything fixed. Great. All right. So, yeah, let's go back to this the query, the simple count, this one that we have done here. Now what I can do is, like, I call this function accuracy. It says, give me a query that returns a noisy value, give me a confidence interval, a confidence parameter, and I give you the error. Okay? So we can run it. Accuracy, and then we'll take this. That was the query. Again, we don't need the real data set. Now you see here the number 1. The number 1 is the stability of the table. And the first table that you have in the system, the one that derives all the transformations and so on, has a stability 1. So the first table ever has a stability 1. Because by definition, remember the HSN definition was a difference of almost 1 in the records. Okay, right. All right, so we go here. Let's say 0.5. 3. With 90% confidence. That's error. It means that, remember that we run this when epsilon was 1. Sorry, we run it here with, let's run it again, when epsilon was 1. Remember it was 10,000, right? 770 plus minus 3. Okay? And now we can start seeing, like, okay, but instead of paying 1, that's too much to pay. I want to pay much less. Remember I told you, less you pay, more privacy, but less accuracy. Now that's error, 300,000. Okay? But you can reason now about privacy and accuracy balances, the trade-off that between them. Again, this is all Haskell expressions, right? All right. Let me show you the key feature, one of the key features that appears in the Dipela that is not anywhere else. And this is about how we compute the accuracy of aggregation, when you add noisy quantities. Okay? And I'm going to show you that with an example. Here we have, like, we are counting over 2 different data sets, whatever that is, and then you add them up. What do you learn from physics? You know, in physics, well, not physics, very basic physics. Like, you know, you measure one quantity, it has certain error. You measure another quantity, it has certain error. Now you add those quantities, what is the error? The most brutal thing you can do is the addition of the errors. Okay? So that is known as a union bound in more formal terms. And I'm a little bit informal, but this is intuition. You know? This is union bound, means like I just add errors. Okay? So in Dipela, we use a theory from probability that is called concentration bounds that says, one is called Chernoff bound that says, if you know that distributions are statistically independent and come from the same distribution, except the parameters of the distribution, if you add them up, the error can be computed in a way more accurate way. But the challenge is how we detect the statistical independence. It means, like, when I sample here, I don't use this value to do the next sample. Right? So I've been working a lot on information flow control. That is all about detecting dependencies and independency of things. So we're going to use taint analysis to detect the statistical independence. Okay? Let me show you how it works Dipela internally. So we have the first query. We'll give you, it doesn't matter the triple here, focus on T1. This is a count, it's a fresh sample. So I put a tag, T1. Right? This is stored inside this value. Then I run the second count. It's a fresh the first and the second count are not related. It's a fresh sample, so I put the tag T2. Okay? Then I do the addition. Is addition statistically independent? No, it depends of two sources of noise, because I'm adding two quantities that come from different sources of noise. So it's not statistically independent, it's tainted. Okay? So now, Dipela will ask, to compute the accuracy of the addition, Dipela will ask, is there one of the operand? If one of the operand is tainted, or there is one tag that gets repeated, if that's not the case, I can apply union bound or the best between union bound or Chernoff bound. Why is the best of both? Because Chernoff bound wins asymptotically, but there are some cases where union bound wins, right? And we are developing a programming language, so we need to consider all the cases, right? So we need to do that. So, yeah. Now let's change the program a little bit to see what happens when this is not, when the answer is yes instead of no. Let's add this scalar. Multiply B1 by 2, that's B3, and we just add them up. Now we have a value, which is B3, we have the same tag as T1, because it was derived from the source noise of T1. Now when I add the three values, there is one tag that gets repeated, right? So then I cannot use Chernoff bound. The best between Chernoff bound and union bound, I can only use union bound. Okay? Let me see how I'm doing on time, to see if we can do. I think I will skip the demo, but for this part, let's do it. I'll do it quickly. Right. So what we're going to do here, just you see the difference between the union and the Chernoff bound. I'm going to do n fresh samples I'm going to call DP count on the same data set, but you can imagine these come from different data sets, just for simplicity. I would say, well, I need to create a list of values somewhere, and I'm going to return the addition of this list of values. Okay? What we're going to do here, we're going to say, well, DP count, EPS, DS. This is the computation that we want to do. But we're going to repeat it n times. And each time is statistically independent, doesn't affect the other sampling. So it's a replicate n. And then I need to do sequence, I guess. So sequence, should make sense, yeah. Right, so we have the query. N counts, and then I add them up. What is the accuracy of that? Right, we say, well, accuracy of total count. Let's do 100. I don't need a data set. Epsilon, let's say 0.5. And let's take the error with 99% confidence. So then we know, it's kind of the worst case. 130. Okay? All right. Now let's do the opposite. Let's do adding the same value 100 times. There is nothing more dependent than adding the same value 100 times, right? So what we're going to do is the do. We say, give me a value, dp count, epsilon ds, return at replicate n v, I guess, yeah. All right, so let's do the same thing as before, compute the accuracy. And now this will only apply union bound, okay? This one in the sample here was applying the Chernoff bound, right? Total count 2. Yeah, correct. Thanks. Almost 2,000. Okay? The good thing is, like, you as a developer, you don't need to worry about it. And if in the addition you have some that are independent, some that are not, Dipela will figure out how to split them and apply the best it can. All right, so these are very simple examples. Can you do more complicated analytics? Yes, histograms. That's the code. CDS, cumulative distributed functions. You can do it like this. You can do it like that. Sorry, like this, like that, or like that. Which one is best? I don't know. You go and figure it out. Okay? You can use budget and accuracy and analyze which one is the best according to your parameters, etc. Okay? So, quickly, I present you the very simplified version of DPELA, so using the Laplace mechanism. But actually, DPELA supports different notion of, different definition of differential privacy. And not all of them are compatible. Not all of them you can cast from one notion to the other one. So the queries are all indexed by the privacy notion, the definition of differential privacy that you are using. Okay? So, to recap, we have a query that we can analyze using the function budget, and that will take the query and will run a symbolic interpreter to obtain what is the budget that the query is using, and it's going to be used by data analysts. Accuracy, which also run a symbolic interpreter, and it's going to be used by the data analyst. And DPEVAL, that actually run the query, and for that you need to set up the privacy budget. That's the data curator. Okay? So, that was the library, 450 lines of code, okay? And in the remaining of the talk, I'm going to tell you some experiences and reflections that I hope it will be interesting and maybe useful for you, how to take this into a commercial setting, okay? So we will change the slide so you know that now I'm talking about DPELA, the company, not the DPELA, the research. Yeah. So, and I'm going to present you the team, the technical approach that we embrace, one of the innovations, and some reflection that have changed the way I think in academia as well as in the company. Right, the team, quickly, is my co-founder, Marco Gavardi, an expert in differential privacy, and myself. We are the founders. We have one business person specialized in business-to-business companies selling to companies. And then my former PhD students who have survived, Agustin and Elizabeth, have survived the education and now join the company. Okay? And then we have some advisory board and some investors. But it's like pretty small. This is kind of I'm pretty academic, so I'm super proud of that. Yeah. Yeah, so the technical approach, we're going to use Haskell. Okay? But we're going to follow 3 principles, which are as follows. We are going to make all the product as embedded as possible. That means let the compiler do most of the work. It will use strong typing disciplines to ensure the correctness of the implementation of the different differential privacy mechanism. And you saw that a little bit when we keep track statically of the stability of the tables. That will be used then to check the noise, and we take that information from the type, right? So we know it's correct. And then we embrace static analysis. We want DPELA to apply as much static analysis as possible. And you saw a little bit of that with budget and accuracy, where I analyze the query without even running it. Right, but this is my well-typed island, right? Which is like amazing. But then we face that, the rest of the world is usually untyped. You get HTTP requests, you get data schema specifications. If you think like, oh, a data set, I represent it with a data type in Haskell. But if the data set is specified at runtime, how you prepare your system to give you any sort of guarantees, right? And then we need to produce outputs which are untyped. But that's no problem because it's from typing to untyping. That's okay. The tricky part is this part. Right. So the product has a strong verification phase, and this comes from normalization by evaluation. It's inspired the name by that. If you know normalization by evaluation, it's a way. Yeah. This is very sensitive, so I wouldn't say it's a way to specialize program. That's okay. It's a way to specialize programs, and there is one aspect of that maps semantic values into normal forms. And for me, the semantic value is the untyped things, right? And the normal forms is we don't have normal forms, but we have data type representation. But we just took the name, not the technique. So I want to be clear. Yeah. So it's a lot of verification phase. All right. Let me show you one technical innovation that we are doing in the company. This is one of the transformations that I show you quickly. DP select. It means like give me a data set and a function, and I will map the function over all the rows in the data set. It turns out that for this to be sound, to this type to make sense, this needs to have sensitivity 1. The Haskell function has to have sensitivity 1. How do you compute the sensitivity on arbitrary Haskell function? Well, people have looked into that. The pioneer of that work was FAST by Reed and Pierce in 2010, where they showed how to build a programming language where you write high-order functions and then you can compute the sensitivity of them. Okay? And that spawned a lot of different work, but they require like what I will call heavyweight programming language theory. Linear types, modal types, dependent linear types, and so on. But remember, we want Haskell to do most of the work, right? So we don't want to just bring another language. So we figured out that it's enough to use parametricity, a certain flavor of parametricity, and then you can get the sensitivity calculations that FAST is doing in the same way. And every time that Haskell type check, Haskell will provide a proof that the function that you've written has certain sensitivity. And this is under submission. All right, to wrap up, some reflections that get me thinking after I started the company. One is about legitimacy. We are academics, right? Right. How does the word legitimate what it means? It means like my boss needs to be an academic, otherwise it will not work. Because my boss needs to have the same experience that I have. I need to admire my work, my boss, right? And that happens in business as well. This is how you organize. This is one way to organize companies called the functional way, where you have different compartments based on certain functionality of the company. You can think that this is your computer science department as well. Instead of product X, say research group X. Then you have marketing, finance, and so on and so forth, right? In business, there is one invariant for organization, which is like research and development. The boss is always one of them because of this legitimacy that I was talking about. Marketing, finance, it doesn't matter. But in research, there are sophisticated people, right? And, that made me reflect about myself, right? So I got to the position where I am, and I guess, like many of you, it's like we are technically strong, we can articulate complex ideas in simple terms, this is what we do down here. But then when we go up, we progress in our academic careers, the type of set of skills that you need are completely different. Right? Are completely different, and there is no way that I could hire someone to fill that gap. Because remember, legitimacy needs to be us. Right? It needs to be us. So we need to train, well, at least I train a lot about some very simple management practices, which is not rocket science, but you need to know them, and it makes completely different. How, completely different. It did for me a completely different in the academia as well as in the company. Right? How you motivate people. We got PhD students that are motivating already from the beginning to work with us. In a company, it's not like that, right? So, yeah. Anyway, so that legitimacy, remember, legitimacy, it's not going to be you who is the boss, but that doesn't mean that because you were famous about writing papers, you're going to be a good boss. That's kind of the reflection. And the last one is about the strategy, you have been in department meetings about, I guess, strategy for the department in the 5-10 years, and everyone is super obsessed about the strategy, right? I'm not saying it's not important. It is important, but there is another factor, which is what I will show you now. This is from a course I did in business where it shows how much a strategy impacts in the success of a firm. It has an impact, yes, it has a big, an impact. But the thing to watch is this. Most 50% of the things that affect your success come from unknown things that you don't control. And when I read that with my mind, academic mind, I said, this is bollocks. This cannot be. And then I started reflecting about how I became a professor, right? My strategy was I want to go to Chalmers, right? I applied, I got rejected. So I didn't get the chance. Then in 2005, I met who was my advisor, Andrew Sabelfeld, in an event. And he said, I'm looking for a PhD student. And the reason that he was looking for a PhD student was because 2 weeks ago, the one that he hired decided not to come. Then I got the position. Then in 2010, there was an opening for professorship in Chalmers, and I decided not to apply. I was confused by them, you know, because I was doing a lot of security. I consider myself a security guy, not a functional programming guy. I have some identity crisis. Now I understood I'm non-binary, right? So I'm both. So I decided not to apply. And then Kun Klassen, a colleague of mine, just when I was going home, I came in the corridor and say, hey, Kun, Alejandro, do you apply? No, I'm not a functional programmer. No, you are, blah, blah, blah. He convinced me, I applied. Did I win? No. I was second. The first one, Dimitro Vitivinois, didn't come, then I got it. All right? So now when I look back at this, I say, well, maybe it's not that bollocks, right? And my reflection is like, have your strategy, but then be exposed to luck. Try to talk to as many people, try to do as many things as possible, because you never know where the lucky part will hit you. All right? And with that, I will wrap up and happy to take questions. Thank you very much.
Can I go? Okay, so if I understood correctly, you're piggybacking the sensitivity analysis on Haskell's type system, but the accuracy and privacy budget tracking, that's a separate static analysis.
That's a different static analysis.
So is there a reason to prefer you doing the sensitivity analysis in the type system instead of also doing a separate static analysis, or?
Yeah, that's a good question. I think what we wanted to do, we wanted to piggyback in the compiler, and if the compiler, when the compiler type checks, the compiler provides a proof. We didn't want to write our static analysis where we need to encode the proof there, right? So we say, if we assume that the Haskell type system is correct, then the type system, when type checking, will do the proof, right? That's the reason.
And then going the other way, is there any hope to do what is currently a separate static analysis in the Haskell type system, or are those things too hard to encode?
That's a good question. This was the simplest way that we come up, that, yeah, why we did like a symbolic interpreter rather than at the type level. Simplicity, I would say. Because I mean, we published this in Security and Privacy, which is a security conference, and then there, it's good when you publish there that you don't put super crazy types. Yeah. So, but it's I don't know. Maybe it can be done at the type level. Everything. I don't know.
Thank you.
Thanks for the excellent talk. So I was wondering about the parallel composition that you mentioned in the background, right?
Yeah.
Are you actually using it? So you had the example with the European and Latin American, right, nationality, but you mentioned in your database you can have both nationalities. What if you could have only one here? Could you apply the parallel composition with your tool?
Right. So, yeah, that's a good question. Let me let me show you how we enforce that. Yeah. Here. So this is what we do parallel composition. It's a partition. So you need to specify up front a mapping for every key that you're going to partition the data, and for every key you give me a function from that partition into a query, and a function that maps. This function needs to be correct. So it means like the thing here can never map one record into two keys, right? And you can see here that that's not the case because yeah, for every record you apply is a function, so then it will map it to only one key.
Okay, so I have to use this function if I want to.
Yeah, when you use partition, that's what encodes the parallel composition principle. Yeah.
I have also just another question. I didn't really understand how you track the budget. Like you had this thing where you gave too much epsilon and it told you, the language told you don't have enough budget. How does it work?
So what we do, we traverse the query and we look for all the measurements. And when you find the measurements, in the simple way that we this is a very simple way to compute the budget. There are more complex ones, but we traverse the query, and then we find all the measurements, and we just take the parameter there.
But does it work if you have different queries, or if I use your evaluate, or does it have to be enforced at the end of the day by the data curator?
Yeah, totally. So
Okay,
the
so
data
it's-
curator will call budget and check, is the budget that this query requires enough? Yeah, they have enough budget. I have enough budget to satisfy this query. If that's the case, then it will go through.
Thank you.
Are there any other ways of preserving privacy than just inserting noise?
Yes.
Or what notion of noise actually in general you mean? There are various noises you can.
Usually, most of the techniques you can, well, there are many, but I mean, in a system like this, if you can sample from Laplace and you can sample from Gaussian, that's about it. Those are the two distribution that most of the people use in the differential privacy community, right? For this type of systems, yeah. So these two are this enough. Is that, sorry, that's what?
Other ways than other than inserting noise.
Yeah. So there are. I didn't talk about it, but there are some what is called data anonymization techniques, which is you take a data set, right, and anonymize it, which means like you make sure, for example, that every time that you do a query with a certain profile, you always return at least k people, or and this is called k-anonymity. But all of these techniques are not strong about what happens in the future. When you anonymize a data set, it could happen in the future. Another data gets available, combine it with this, then you de-anonymize the people. So there are techniques, but for me, this is the gold standard, right? There are other ones that even industry uses, but they are not strong against this future protecting privacy.
I have 3 questions. You can answer any one of them. So first one, following up on previous one, is what if we about the about the precision of the accuracy, for example.
Yeah.
So you very often need amortization techniques in practice. Doesn't seem to be the case here.
You-
For example,
yeah.
amortization techniques. So for example, if you had the query there, it says like, you got Europeans and whatever, Latin Americans, and before actually going to the output, you actually eliminate the duplicates, okay? So do you get, what's the accuracy of this one? Because this is basically identity function now, so you should have 1, right? But what do you get here from the analysis?
So
That's the first question.
yeah. Well, in that system we don't do that. In the company we do that. So in the company we do more. We put more static information on the transformations, so then to deal with these kind of cases.
So in that case, you would get actually that it's just basically identity. So it has accuracy, or it has a budget of 1 as opposed
That's
to
right.
2.
The sensitivity of 1. Yeah.
Sensitivity.
If you remove, if you
Oh, that's-
remove duplicates when you do the union,
Yeah.
right? Yeah.
That would be really interesting to see, but I guess you have a company for that reason.
Yes.
The second part is looking at these things. Actually, database systems have 2 things that are really, really cool, I think, and are very important, namely atomicity and transaction. So concurrency control, you wouldn't leave that to an application program. And the other one
Totally.
is join queries. So there's no joins in there. So
No, joins are tricky because when you do join, the sensitivity. So when you do a join, the sensitivity can go to a roof, and people have looked into many different ways to address this problem, and I'm not convinced about any of them. So we don't have it. So what we say, on the company side, we say to customers, is like, give us the whole data set, and that's usually the case so far, right?
last question.
Yeah.
What was your pitch? You have 30 seconds up the elevator. You had actually 2 VCs there, and they will actually not look at this. They will say like, what's the business value? What's the business pitch?
Right. So what we say is like we do analytics on personal data without compromising privacy, and this will be needed. Yeah.
Where's the market?
Right.
who are the
I
customers?
was going to that. Yeah. And that's what we needed for most of the B2B businesses that are collecting personal data aggressively today, and the market is projected to be around 20 billion or something. I don't remember the numbers right now, but I can give you that. Yeah. So it's a it's a analytics market, GDPR regulations market, data masking market. This is the target addressable market, service addressable market, service obtainable market. Yeah. So you know about that. Yeah, thank you. Yeah.
Yeah, thanks for the talk. So one question that I had was, you compute the sensitivity in sort of a compositional way here, and you do this by letting the user, the programmer, specify how they want to spend their error budget, right?
Right. The privacy budget. Yeah.
Yes, the privacy budget. Now, you could consider an optimization problem, which is that you want to get the best possible accuracy for your total budget.
Totally.
So have you considered this, maybe by computing some kind of a program transformation that gets you a function of the local budgets, giving you the total accuracy?
Usually, you know, to squeeze from the same budget to squeeze a lot of accuracy, it requires to go into algorithm design, right? So which is not something that I haven't seen how automatize that. You know, here is pretty simple, but you know, one of the things that you know, when I show you 3 different ways here, I'm rewriting the algorithm in a different way to squeeze out more accuracy with the same budget. But you need to go into writing code or designing algorithms, right? So I don't see as an optimization, you know, you come with a problem and, you know, I haven't seen yet patterns where, you know, it's clear to say, oh, do this pattern, then you will squeeze out more accuracy from the same budget.
All right, yeah, I wouldn't expect this to happen push button automatically, but you could at least try to compute some kind of a function of the local privacy budgets from your original source code, and then use some different analysis on that. If that makes sense.
Yeah, no, it makes sense. I mean, it makes sense. I don't see. Yeah. No, it totally makes sense what you say. But I think this is part of the future research, I guess. Yeah.
Right. Last question. Any more? Right. If there's no more question, let's thank the speaker again.
Thank you.
All right.
Thank you.
Thank you. Right. Okay. So this is the beginning of our contributed talks, and the first talk of today is given by Ran Fukaishi on productivity verification for functional programs. Thanks.
Hello. Let me start my presentation. And this talk is about automated verification for productivity for conjunctive data structures. Productivity is an essential property of conjunctive data structures. And conjunctive data structure is, in general, infinite data structure, such as infinite lists, also known as streams and infinite trees. Productivity means that each element of the data structure can be generated eventually. For example, the first line defines infinite lists consisting of infinitely many ones, and this is a productive definition. But the second line is not productive because the head function requires that S has already generated at least one element, but it doesn't. So the element of the second stream are never produced. And we proposed a new productivity verification method by reduction from productivity to termination. I'll consider more tricky examples, which we call left tree and right tree. The definition of the left tree is here. Node is a constructor of the binary tree, and left is a destructor which retrieves the left child. A left tree is not productive because we can't generate the left child. Let's try to generate the left child. We can unfold the left T, and we can price the destructor left, but it coincides with the original term, so we can't generate the left child. As a result, left tree represents a non-productive tree in this figure. Next, the definition of the right tree is here. Right is the destructor for right child. And on the contrary, we can generate the left child of right tree. We can unfold the left T. We can apply the destructor right. We can unfold the left T again. Then we can calculate the label of the left child as 1. So right tree represents a productive tree in this figure. Let me discuss some related work. One of the main approaches for productivity verification was type-based. Type-based method counts the number of constructors and destructors. For example, the left T inside the definition of the left tree is applied one destructor left and one constructor node. Since the numbers are same, the type-based approach rejects this definition. And this is fine because left tree is indeed non-productive. But it also rejects the definition of right tree, although it is actually productive. So previous type methods is too conservative. The productivity of term writing system is also studied. For example, Andrew et al. Proposed a reduction from productivity to context-sensitive termination. But the approach can't use an ordinary termination checker. Also, the approach doesn't directly support higher order functions. This is the outline of my rest of my presentation. Let me overview our method. Our approach is reduction from productivity to termination. We consider a functional program with conjunctive data structures as a source program. Given a source program that generates a conjunctive data structure, we translate it into a function which takes a path which represents a position of the data structure and returns the corresponding element. So the target program no longer has conjunctive data structure, and a conjunctive data structure in the source program is productive just if the translated program is terminating. So we can use off-the-shelf termination checker and non-termination checker for productivity verification. As I said, we translate a conjunctive data structure into a function which takes a path and returns a corresponding element. A path is represented by a sequence of destructors or integer list. I'll explain it by using an example of a binary tree. We first regard a path as a sequence of destructors. And we can get corresponding elements by applying the destructors left to right. We can also regard a path as an integer list by converting destructor into an integer. In this case, projection 0 is converted into an integer 0, and projection 1 is converted into 1. Then we can consider a conjective data structure as a function like this. In this way, we translate a conjective data structure into a function. I'll introduce a detailed idea of the translation through the examples of left tree and right tree. Left tree is translated into this recursive function t. Here, the constructor node is translated into this function. It takes a tuple consisting of the function L corresponding to the left child, and label x, and the function R corresponding to the right child. Then it takes an integer list as a path and perform pattern matching on it. If the argument is null, it returns the label x. If the list starts from 0, it refers to the component of the left child, so it passes to the it passes the remaining path ls dash to the function L. If the list starts from 1, it refers to the right component, so it passes the remaining path to the R. Otherwise, the argument list doesn't represent any position of the data structure, so it returns the meaningless value 0. The destructor left is translated into this function. It extends the path by integer 0. And we can verify the termination, the non-termination of the function t. So our method can verify the non-productivity of the left tree. And similarly, right tree is translated into this recursive function. The destructor right is translated into a function that extends the argument ls and passes to the function corresponding to the parent. And we can verify the termination of the function by a termination checker. So our method can verify the productivity of such an example. Now let me sketch formal definitions of the source language and target language and the translation. Our source language is call by name random calculus with conjunctive types. The non-functional type denoted by sigma includes integers, products, sum, and recursive types. A conjunctive type is represented by a fixed point type denoted by new. For example, the type of stream is represented by this, and the type of binary tree is represented by this. The type denoted by tau is either a non-functional data type or function type. So we do not allow functions stored in conjunctive data structures. The term denoted by M is those of standard random calculus with fixed points. And the recursive definition of the conjunctive data structure is represented by using a fixed point operator. For example, a right tree explained before is represented by this term. Now let me explain the definition of productivity. We define a term n of type sigma as productive if for every pulse gamma to access an element, gamma m is terminating. Here, gamma m denotes the term obtained by applying the corresponding destructors. For example, a stream m is productive if and only if these terms are terminating. And it is equivalent to the statement that for every I, the ith element can be calculated eventually. The target language for our reduction from productivity to termination is also called by name Lambda calculus, but it doesn't contain coinductive data because they are translated into functions. Instead, the target language has primitives on integer list so that we can express paths. The terms of the target language contains primitives on integer lists such as new, cons, and pattern matching on lists. Our translation is type-directed translation. The judgment of the translation is quadruple relation. Gamma is the type environment, and M is the original program, and tau is the type of M, and N is the translated program. Let's consider an example here. Suppose X is a variable of stream type. Pi0x represents the head of the stream X. It is translated into a function like this. This function returns the first element of the stream if the argument u is null list. I'll introduce some translation rules. Lambda abstractions and applications are translated recursively like this. A pair is translated into a function as a constructor node. If the argument u is null, it returns the label of the pair constructor, and it is a default value 0. And the first element of the u is 0. It refers to the component of the left child. So it passes the remaining path u dash to n0 obtained from in m0. If the list starts from 1, similarly, it passes the remaining path u dash to n1. A projection is translated into a function as in the destructors left and right. Now I'll explain the correctness of the translation. Our translation is sound and complete. The theorem states that the original program M is productive if and only if the translated program N is terminating for all input list. Due to the soundness and completeness, we can verify not only productivity but also non-productivity via termination and non-termination checker. Then I'll talk about implementation and experimental results. As I said, productivity and non-productivity are reduced to the termination and non-termination problems. We implemented a new termination checker because there's no termination checker that supports integer list primitives and whose performance is sufficient. The termination and non-termination problems are further reduced to the validity problem of higher order fixed point logic for short HFL. HFL handles higher order predicates and fixed point operators. We generate two formulas that correspond to termination and non-termination. There is a HFL solver named mu-HFL that can handle integer primitives. We extended mu-HFL with integer lists. As a result, we can check productivity and non-productivity in this scheme. We conducted experiments on this table. We used mainly our original benchmark. And this column shows the time for verifying productivity or non-productivity. And this column shows whether the size type system can prove productivity. The table contains right tree and left tree explained before. It also contains a Fibonacci stream as a higher order case. TI ranges over natural numbers, instances that are productive if and only if I is even number. So our tool can verify, our tool successfully verified all test cases except T1 and T38. So our tool can verify some instances that previous tools can't handle. But the performance is low in some cases. First, the performance for refutation, such as left tree and T1, is low because our non-termination checker can't find counterexample efficiently. Second, the performance for higher order case is also low. The improvement for these cases is our future work. Let me conclude my presentation. We have proposed a method for reducing productivity to termination verification for functional programs without conjunctive types and proved its correctness. We also implemented a prototype productivity checker based on our method and conducted experiments. Then we confirmed the effectiveness of our method for some instances that previous tools can't handle. In future work, we aim to support other properties such as safety and liveness. We also implement our productivity checker for actual programming languages like Haskell. Thank you for listening.
We have time for a couple of questions.
There are no other questions. So you define the notion of productivity in terms of termination. And then, to me, it's not a surprise to get then at the end a sound and completeness result. If you have defined the notion of productivity according to another property, then what you would expect, again, sound and completeness results? Do you see my question? If you put up the slides on productivity, when you define it in terms of termination.
Actually, we can define productivity as convergence into infinite term, but we can't we can't directly handle such terms, so we define productivity by termination.
It was just an answer to your question to the man. I don't know your name. Alberto.
So suppose that I have an interpreter for some programming language, and I enumerate a tree that contains all of the possible input for this interpreter, and then I fmap my interpreter onto it, and then I ask whether or not this procedure that produces this tree is productive, right? And then certainly I cannot. Right? So it's so I suppose you will get undecidability for this reason alone.
But if you put up the slide on productivity, can you put up that slide? When you define, you could have chosen to put up the research topic, so to speak. You could have chosen another definition of productivity in terms of another property, not termination, and see how this relationship between productivity and this other property could be defined.
So I can actually answer because I've worked on similar problems in the past, and usually at least what we did is we define productivity semantically as, because it's a conductive definition, so you define it as the final coalgebra of some functor, and then you reason about the objects in this final coalgebra. And if these objects are finite, infinite trees, then your term is productive.
Okay, so my question's a follow-up on this one then is, if you go back to the table, please. So imagine now we have a definition that says there's a
Yeah, I saw the audio before. That's why
Are we getting sound mixer?
yeah.
Okay, perfect.
Different. That's it. Yeah. 1 2 1 2. Did you hear it? That's so fine. Okay, so the audio is just gonna. Yeah. So the audio is just we're putting the Oh, I see. Are we swapping? No, it's just the microphone. It's just gonna aim at the laptop, and that's it. Yes, the volunteers.
Okay. Is it working?
Not
No?
really. It sees the display.
Do you mind if I check it itself?
Oh, okay. It's working. So I'm doing it now. Yeah?
No.
Okay.
Okay, let's get started. Welcome to the second session of PEPM 2024. In this session, we will have 4 talks. And our first speaker is Tomoaki, who will be talking about a library for stream processing. And this paper was selected as the best paper, distinguished paper of this year's workshop. So congratulations. Okay, so please start your presentation.
Yeah. Thank you for the introduction. I'm Tomoaki Kobayashi, a master's student at Tohoku University. This is a joint work with Oleg Kiselyov. Today, I'm going to talk about a paper, Complete String Fusion for Software-Defined Radio. In this research, we evaluated stream-on-us by software-defined radio. Stream-on-us is a declarative stream processing embedded DSL, an implementation given by OCaml, and it can generate efficient C code. This feature is thanks to complete string fusion. Let me show an example. Stream-on-us from the left declarative pipeline can generate the right imperative efficient C code. This C code is efficient because it has a single main loop and no dynamic allocation at all. In the past, stream-on-us had evaluated only by small micro benchmarks, and we didn't know complete string fusion is whether complete string fusion effective in realistic applications or not. So in this time, we evaluated stream-on-us by large macro benchmarks of SDR. Especially, our goal was to confirm performance on real-time FM radio reception of stream-on-us. FM radio reception is described like this. Now, as I input, FM signal is given. Typically, it is in 1 to 100 mega samples per second, and it is processed by low-pass filter and FM demodulator, and finally, it is passed to sync, typically in 48 kilo samples per second. In this research, we implemented FM radio reception of stream-on-us like this. And this implementation corresponds to FM radio reception of the most popular software-defined radio framework, GNU Radio. So low-pass file source, low-pass filter, demonstration, and null sync. With the basically same pipeline as the result slide, we can listen to actual FM radio on stream-on-us. Now I play back a pre-recorded result of a Japanese local station. This is a noisy but certainly intelligible result. Upon realizing this application on stream-on-us, we encountered a challenge. That is, stream-on-us doesn't provide windowing. Windowing is a combinator which takes a stream as an argument and returns a stream of window. Window is a history of recent data and required by many digital signal processing operations of software-defined radio. This is such an operation, FIR filtering. Here, Xi is the current input, and yi is the current output. Then when computing yi, m samples from xi minus m minus 1 to xi are required. And with windowing, streamless filtering can be implemented like this code. Windowing on XS, then map. This is what we wanted to do. So the accompanying question are as follows. Can we express windowing with the current streamless? Does it require an extension to the existing primitive combinators of streaming? And in that case, what about complete fusion of windowing? And if we can express windowing, then does the expressed windowing have high performance? Is it sufficient for real-time radio reception? We addressed the challenges by designing a high-performance windowing. It guarantees complete fusion by construction. Using this windowing, we evaluated streamless by FM radio reception on a relatively low-end platform, Raspberry Pi Zero. And it was faster than the state-of-the-art GNU radio, and it attained real-time FM radio reception. This is how we addressed the challenges. Streamless supports by nature stateful streams. So it means streamless can handle state-free Windows history management. And its existing primitive combinators turned out sufficient to implement windowing. That is not to say easy. A lot of effort went to generate C code that is optimal or optimizable and vectorizable, as I will explain later. And since we managed to express windowing via existing primitives, complete fusion is assured by construction. For windowing, we generate the code specialized to window size and sliding or tumbling. There's no time to go into detail, so let me show just a simple example. Cyclic buffer is a straightforward implementation of stateful window. In this case, access to a buffer in generated code becomes an operation of I loop index I and bit mask. And this access is too complex to automatically vectorize by C compiler. And under some specialization conditions, we generate a windowing code whose Windows allocates buffer twice the needed size and copy from time to time. In this case, all loops have constant bounds, and all index expressions are I plus const. This is easy to optimize and vectorize by GCC or clan. Now we have a high-performance windowing. Using it in evaluation, we compared Streamonas generated C code and GNU Radio C++ code on Raspberry Pi Zero. There are two types of evaluation. One is FM radio reception benchmark. This uses the application on the result slide, and its source loads a file of pre-recorded 3 seconds FM signal, and sync just throws away its input. So it means it do nothing at all for input. And another evaluation is real-time FM radio reception. This it uses basically the same application of the benchmark, but source and sync are different. Now source becomes an SDR receiver connected via USB, and sync becomes an audio player. As for FM radio reception benchmark, this was the result. There are two variations for source of the pipeline. Preload means preloads the whole file while the reception. And include means incrementally loading the file block by block while the reception. And all runtimes were less than the loaded file's 3 seconds. And as you can see, Streamonas was twice or more faster than GNU Radio's runtime. This is the result of real-time FM radio reception. Streamonas had a little unstable and noisy, but intelligible playback. And GNU Radio had unstable, noisy, and unintelligible playback. Related work is as follows. Streamito is a standalone DSL of stream processing. Its execution model of stream processing is based on static scheduling and synchronous data flow. And it has split and join operators for streaming. On the other hand, Streamonas is an embedded DSL, and its execution model is based on push and pull-based streaming. GNU Radio is a state-of-the-art software-defined radio toolkit, and it is actually a C++ framework. We can use GNU Radio by writing C++ code or Python binding code, or drawing block diagram in GUI toolkit. When using block diagram, GNU Radio generates C++ code or Python binding code internally. Unlike the Streamonas' code generation, GNU Radio's code generation has little type safety, and bugs are easy to introduce. And GNU Radio's processing is scheduled by thread per block scheduling. So it means it has multi-threading. On the other hand, Streamonas processing runs on single threading. In conclusion, we designed a high-performance windowing and evaluated Streamonas by FM radio reception on Raspberry Pi Zero. as for future work, there are many things, but what I want to try right away is high quality sound real-time FM radio reception. This is the end of my talk. Thank you very much for your attention.
Thank you. Any questions?
Do you have a little recording of your things you presented to us, the 5 seconds music or whatever? Do you have the improved version of it? Is my
Sorry.
During your presentation, you make us to listen to 5 minutes or the 5 seconds music or whatever. 10 seconds. Do you have the same thing after your processing? You're improving, throwing away the noise of that.
Was the best version? Was this the best version?
Yeah. Yeah.
A lot of noise in that. So can you reduce
I
that
noted
noise?
that.
Not with picture, with sounds.
This noise is due to this live sound processing, and we haven't tried high.
Okay.
Yeah.
Now
high
you
quality
process
sound.
that, you improve that, the quality of that broadcasting. Can you make us to listen to the improved broadcast?
But I think you haven't actually done this future work. Improving it is future work, if I understand.
So currently you have the versions of noisy So currently you have the noisy version of the FM radio, right? So do you have you applied your tool on this noisy FM radio to show the difference between the baseline and your improvement? Yeah. So.
I think what he's trying to say is that GNU radio produces the same noise due to naive audio processing, and actually the result is that his method is faster, not that it produces less noise.
Okay.
I'm not sure. I'm not so good at English conversation. Sorry.
So the improvement is that your audio processing or your streaming is faster. Your stream processing faster, but you're not producing less noisy radio signal, right?
I may be sure what you are asking for me. So for high quality sound processing, it requires speed, but my current implementation is so slow, and you consider this is a kind of issue, maybe not?
Sort of.
Sorry.
Yeah. Okay. So the question is sort of your streamonas processes the signal faster than GNU radio, right? But it doesn't reduce the noise. It has the signals, the output signal of GNU radio and the output signal of streamonas as the same signal.
With the same input, GNU radio.
Yes, the same input, but it's not the same output.
With the same input, GNU radio and streamonas generates basically same input without computation error.
So only speed is improved. Only speed is improved. Is it correct?
Yeah, actually.
But
yeah.
as long as the speed is enough to follow the human conversation, and don't need faster processing. You see, there is an intrinsic limit. It's not necessary to go faster and faster as long as you keep up with the pace of signal of human voice.
Okay.
Or whatever. Maybe, okay, yes.
GNU radio result was unintelligible, so speed is, in this case, is so important.
But unintelligible is not a physical quantity. You have to tell us the power of noise. A number is necessary. Unintelligible is because maybe it's another language, it's English, I'm expert in Italian. Unintelligible is not a physical measure.
Thank you. Would the same approach work for AM or shortwave broadcast? You can listen to it here, like BBC shortwave in London. Do you have to have some special hardware to do this?
You mean you tried BBC radio reception?
Now?
Here?
Yeah.
I haven't.
Haven't
yet.
tried. Oh, okay.
Yeah. But I want to later. Check it.
Any other questions? So we have this certificate of this award. So congratulations again. Okay, thank you. So let's move on to the next talk. Hey, なんか写真撮りたいって。Okay. Okay, our second speaker is Igor. He will be talking about functional conversion in mini-current. Please start.
Welcome. My name is Igor Engel, and today I will be talking about a case study in functional conversion and mode inference in mini-current. So, to set the stage, let us consider the problem of program inversion. So, given some program that computes output from the input, so y from x, we can construct an inverse program that converts output of the first program to possible inputs that this program would evaluate. So, for example, if we have a program that does type checking, we can invert that program and automatically get a program that does type inference, given that it knows that the type should be correct. There are multiple ways to approach this problem, and one of those is inverse interpretation, where we have some interpreter that can take an original program and just run it backwards without actually conversing it. And one of those possible interpreters is a relational language mini-current. So if we have a program in mini-current, such as an example here is addition relation between two numbers, we can run it forwards. So we know x and y, and we want to evaluate the value of z. Or we can run the same program backwards. We know the value of z, and we want to find all possible values of x and y that satisfy this relation. And we can use relational conversion to take a program in some other language, such as Haskell, convert it to mini-current, and then evaluate it in a backwards direction. But there is one problem with this approach to program inversion. It is slow. Because our relation in mini-current, it can be run in all directions, but the outputs of relational conversion ends up optimized for forward direction and runs very slowly in others. So we introduce here a functional conversion which takes a mini-current relation in a specified direction and outputs back a functional program. So we can take functional program and convert it directly to any other direction that would work. And we hope to generate the same answer that running in mini-current would, and hopefully do it much faster. So to introduce mini-current as a language, here we have a declaration of a relation addition between three arguments x, y, and z. And it can be called recursively within itself. And basic operation of mini-current is term unification. So we say that variable x in this case must be equal to 0, and we can conjunct those unifications and calls, and disjunct them as well to produce various combination. So here we have an addition relation that says that either x is equal to 0 and y is equal to z, so 0 plus y equals y, or x is a successor of some number, and x minus 1 plus y equals z minus 1, and we add another successor to get z. And here example of a functional conversion that we would perform on it. So given our addition relation, we construct this function that behaves basically the same way. Also, when we invert the program, we want to consider that non-injective functions end up as non-deterministic conversions. So if we have multiple inputs that end up as the same output, in the end we will have multiple outputs that result from the same input. So here, for example, there are two possible ways to find x and y that add up to 1. To represent this non-determinism in the result, we use streams, which are list-like data structure that does interleaving search that guarantees that all branches of the stream will eventually be examined. So, and the implementations of Minikaren also use stream internally, and Minikaren is implemented as a stream of substitutions on logic variables, and our functional conversion will be implemented as a function returning a stream of values. So here's an example of functional conversion in a backwards direction. Starting from absolutely the same addition relation, we get a different function, one that, given a number, finds all decompositions into a sum of two numbers. Here we can see that it proceeds as follows. We can always decompose the number as 0 plus itself, and if that number is non-zero, we can take all previous decompositions and shift one of them, a unit in them, to the left side. And we can also consider the following directions where we only know x variable, and we want to find all possible answers to what happens if we add y to it. In Minikaren, this would result in a following substitution, that z is a successor of y, and it produces a single answer that has a free logic variable in the output. We can't allow this in a functional conversion because functional languages have no idea what a logic variable is. So to solve this, we introduce generators, which are a stream of values that we pass into a function that produce all possible values for a given type. And here's an example of a conversion in this direction, and it produces an infinite stream of answers. So 1 plus y is 1 plus 0 is 1, 1 plus 1 is 2, and so on. While Minikaren would only output one answer, but it would be incomplete. So, to introduce our conversion scheme, we will start with Minikaren relation, normalize it, perform mode analysis, also known as binding time analysis, in a specified direction, and then convert this into intermediate language that serves as a bridge between Minikaren and functional languages, and convert that intermediate language into a functional language, such as Haskell or Camel. For normalization, we want to simplify Minikaren relation as much as possible, and basic steps is to remove nested constructors and repeated variables. So each statement uses each variable only once, and each unification will in fact be a variable unified with possibly a single constructor. And we also normalize the relation itself to be in disjunctive normal form, so disjunctions on top and conjunctions within them. After this is complete, we proceed to mode analysis. So we have two possible labels for variables, ground terms and free variables. A free variable corresponds to a free logic variable in Minikaren. It has no known value at this point. And the ground term has some concrete value. And once a variable is assigned a value, it always has this value. So a mode is a transition between those two states. We have input mode where we already know the value of our variable, and an output mode where variable was previously free but is now assigned. This ends up separating single unifications into 4 possible types. So if we want to assign a variable x to some term, it's an assignment operation. If we know two values and we want to ensure they are the same, it's a guard operation. So it's a check that both values are the same. If we have some variable that is unified with the term and we already know the value of a variable, it's a pattern matching operation. And if we don't know the value of a variable and also don't know what happens on the right side, it's a generator operation because we have to generate some set of all possible values. So to perform a mode analysis, we also have to reorder conjuncts within the relation to ensure that the data flow is correct. And turns out there are multiple possible ways to order the conjuncts that result in a correct data flow, but not all such ways are equal. So here's an example of multiplication relation, and it has two calls within itself, a recursive call to multiplication and a call to addition. And depending on the order of these calls, the performance of converted relation dramatically changes. If we put addition first, we eventually enumerate all possible candidates and then just check whether any of them happen to be a multiplication, which ends up being very slow. But if we want to put multiplication first, we produce the right answer immediately. To solve this problem, at least heuristically, we have a priority for possible types of operations that is generated basically by how likely they are to produce a lot of possible values. So guards, assignments, and matches don't produce more than one value in any case. Then we have a recursion call in the same direction, which is usually produces only one value, or at least as least values as needed. Then we have other calls where some arguments are ground. Only after that we introduce generators, because generators will produce all possible values for a type. And only after that we have calls where all arguments are free, because those are usually generators but for multiple values. Here's an example of our multiplication relation. We will notice that call to multiplication will in fact be a direct recursion, and will produce a very limited amount of values and place it first, resulting in the fast order. So after we have complete mode analysis, we can introduce a functional language, and it has minimal operations needed to represent minikernel. So we have interleaving of streams. We have a monadic bind on streams that represents computation. We have construction of a singleton stream, a quality check between values, pattern matching to remove constructors, a function call, and the call to generators, which is separated syntactically. And to translate our moded relation into this language, we convert disjunctions into interleaving, conjunctions into bindings, and calls into calls, and unifications into one of four possible operations depending on their type. And to solve the generators problem, if we have encountered a generation within the relation, we pass this generator as an argument, an additional argument to this relation. And also, of course, pass it to all recursive calls and as such. So here's an example of our addition relation. Because it ends up with y variable free in output, it needs a generator for y variable, which gets passed as second argument and used in first case of this function. And also, generators are of course transitive, so if any call within our relation requires a generator, it also gets added to the arguments of our relation. And let us consider the example of relational sort. So here we have a relation of sort implemented in minikernel as basically a definition of a sorted list. So a list is sorted when first element is smallest of the list, and the rest are sorted as well. So here a relation will decompose smallest arguments of a list, sort the rest, and construct it into the end. And this relation can be run in both directions, so to sort a list or to generate all permutations of a sorted list. But depending on the order, one of those directions will be very slow, even in relational language and in functional conversion as well, if we don't handle directions. But we do handle directions. So here's an example of speed up. If we have a slow direction for sorting, we end up timeouting, which is like 300 seconds on a list of 5 elements. In the right direction, we can sort up to 32 elements in relational language within a second. And in functional language, the same operation takes 1,000 for a second. And we can get up to 262 elements within a second of sorting. And we see the same feature for generating permutations. So here the orders are swapped, and we also time out very fast if we have the wrong order, and time out relatively fast if I have the right order, and functional conversion still beats up relational interpretation by orders of magnitude. And there are also multiple possible speedups of functional conversions that are currently not yet implemented but are further work, which is determinism checking and partial deduction. So if we have some multiplication, here's an example of multiplication relation. If our arguments are non-zero, there is in fact at most one answer possible, and at most one answer in every branch of computation. So we don't actually need streams here to model the non-determinism. And the beauty of our Haskell translation of this is that we can just replace the type of this function without changing any of the code, change the monad it uses to maybe, and that was tenfold speed up. And one of the goals of our further work is to check when we can do this automatically. And another possible speed up is partial deduction. So when we have, for example, relations that evaluates Boolean formulas, and we want to check whether they evaluate to true, and then we want to invert it and generate all formulas that evaluate to true. We can in fact embed this true in relation using partial deduction and invert the deduced relation, which ends up significantly smaller than the original and such faster. So in the end, we have a functional conversion scheme that converts from a minicanner relation into a functional program. We showed that this speeds up considerably relational programs, and as such can be used as a form of program inversion. And we have an implementation of this conversion scheme in Haskell, so we can in fact convert any minicanner problem. Our current work involves determinism check and partial deduction, and integrating our conversion into a framework of relational interpreters. I'm ready for questions. Thank you for your attention.
Thank you. Question.
You introduced this data type stream, which was an instance of monad.
Yes.
Correct. Okay, so the bind operator for your stream is this interleaving operator.
It's like a bind operator for list, except instead of concatenation, we use interleaving. So the relevant part of streams is that a concatenation of streams is in fact their interleaving. And from this follows the monad representation.
Yes, but interleaving is not an associative operation.
Yes, so we technically violate some monad laws, but it works in our case.
Okay, so in what sense is it a monad? If I view the output type as a set, or
well, it's we do implement it in Haskell as type class monad. It does violate some laws, but some native Haskell monads also violate some laws. So it's almost a monad.
Okay.
And we use monad-like operations on it.
Okay, thank you.
Could you go back to the slide with add IOO? Yes. So you have only one generator there, right?
Yes, because we can infer the second variable from this generator.
So can you explain that again, how you basically eliminate the second generator by
the generator here comes from this unification here, y equals z. And we know that z will have the same value as y. So we don't actually need a generator for z because we know it will have the same value as a generator for y produces.
Thanks.
So your relations are mostly in like first order ones. What about if you have some kind of relations that are not functional? If the recursive definition, if the predicate occurs on the left of implication,
in fact, interleaving is what solves this. So minicanner has some guarantees about termination. So it will minicanner will find all answers to a relation. If you try to request more answers from it than it has, it might not terminate, but it will produce all possible answers. And our functional translation has the same guarantee. So if you take a finite look at the stream, it will eventually produce all possible answers, but it might not terminate.
Okay, thank you.
If I give you a lambda expression, maybe say normalized, can you predict how hard it will be to invert? There's some properties that make that you're aware of that make it hard to invert. Say, if I give you a pseudo-random number generator, and you want to recover the seed, or what are some features that you can describe that make it hard to do this?
So in the end, it will be inverted, but it will be very slow because it will eventually just have to enumerate all candidates. And to describe from a relation, from start, it's a hard problem to just describe something like this. I haven't particularly delved into which programs will end up being slow in inversion. So you can have some facts like, so we know that type inference for type systems is much slower than type checking, and this will of course be revealed in the inversion. To say this in general is, I'm not sure how.
Okay.
So we know some examples will be hard. It's how to say, how to tell this in general.
I see. Can you relate this work to other kinds of reversible computation, say Toffoli gates or different kinds of models of reversible computation?
So a lot of this depends on how we do relational conversion, which is not part exactly of this work. It can be attached separately. There are multiple possible ways to convert a function into a relation, and this will end up informing much of what goes on, because minikaren basically specifies a lot about how we will evaluate it, and basically the only freedom we have in our translation is ordering of conjunctions. And this produces sometimes slow down, sometimes speed up. And so basically we have a lot set up by a relation we have on the input, and we can sometimes improve on that, but not much, and mainly we try to avoid slow down relative to a relation while eliminating overhead.
Thank you.
Any other questions? No? So I have a question. You have been focusing on minikaren, and I was wondering whether you can apply your approach to relational programming languages other than minikaren.
Yes. So minikaren is in fact particularly simple. There's very few operations. Minikaren is very pure relational language, so we don't have any operations here that influence evaluation order and such. And so for minikaren, it's easy to preserve the guarantee. For other relational languages, you can do the same translation, but it will be harder to prove that it guarantees the same things as the original.
Okay, thank you. No more questions? Okay, let's thank the speaker again. So our third speaker is Luis, who will be telling us about how to apply partial evaluation to reversible flowchart programs.
Yes. So hello everyone, my name is Louis, and as I mentioned, going to talk about partial evaluation of reversible flowchart programs. This work was done in collaboration with Robert Gluck at the PLT section at the University of Copenhagen. So for some background information, there are two fields we concern ourselves with here. Reversible computing stems back from the 70s. And for the sake of this talk, the important concepts are the fact that a reversible program needs to be backwards deterministic, which means also that we can only work with injective functions. And also it'd be nice to be able to efficiently invert a reversible program, thereby getting the inverted program. And it has a bunch of interesting areas of application. Also, for the sake of this talk, in partial evaluation, we also concern ourselves with flowchart languages, as they are seen as very versatile and therefore foundational in some sense. However, despite both of these areas being stemming from the 70s, it's only actually very recently that work has been done on combining the two by Torben Mogensen, also from KU. So therefore, the goal of our paper was to aid in this foundation of partial evaluation of reversible programs. And by that, we have fully formalized a partial evaluator for a reversible flowchart language. We have done a complete implementation that is also publicly available on GitHub. And we have done some interesting experiments composing program inversion and partial evaluation, which we will hopefully get to later. So the plan for today is to talk about a few of the highlights. First of all, the RL language, which is what we've worked with. I will talk about some of the trials and tribulations of doing partial evaluation here in this new paradigm. We will hopefully show a result and then also talk about these experiments. So first of all, we here see an RL program. On the left-hand side, we have the textual representation, and then on the right-hand side, we then have what it would look like as a flowchart. This is the Fibonacci pair program, which is to say that we take an input n, and then we then compute the nth Fibonacci pair. The pair is, of course, needed for it to be injective. And if we were to just look at the flowchart version, this is actually kind of a loop structure where we go in from the entry, and then we n times repeat this loop where we decrease n by 1, add b to a, and then swap the two, until finally we get the Fibonacci pair. And just for the sake of it, we have the flowchart version here. I said we want this to be easily invertible. So the way you invert an RL program is by simply inverting the flow and then thereby swapping the places where we split and where we join, which actually maybe I should elaborate on. So these diamond shapes are the traditional conditional jumps we have in programs. However, since we want to be backwards deterministic, when we join our control flow, we need what we call a come from statement, which simply is analogous to the conditional jump statement where we have an expression, and depending on the value of that expression, we know whether we came from one side or the other. And they are, in fact, so analogous that when we invert them, we just swap them around. And by inverting the control flow, we also need to invert each step. And this is actually, I might skip a bit through this because the precise semantics are not too important, but we have reversible assignments with some expected C-like semantics, except that for the sake of injectivity, we cannot have the left-hand variable occurring on the right-hand side. For example, x minus equal x is essentially setting x to 0, certainly not injective. We have a form of pattern matching. Importantly, patterns must be linear. And finally, we have some assertions, which will become very useful later on, which also have the expected semantics of having a runtime error if we have a false value. So, traditionally, partial evaluation, we are talking about specializing a program with respect to some statically known data. And for the rest of this talk, we will be showing the static part using the color blue. And the dynamic is the unknown, the thing that will depend on the runtime program. It'll be red. Then we will do a state collection, where we run through the program with this static state and obtain all the different program points. And we then specialize each block of code with respect to this static state, generating some residual code. And then we do some post-processing, such as transition compression, to make it nice and tidy. However, in the reversible setting, just doing this will cause some troubles, some of which we will go through now. For example, a reversible program requires to only have a single exit point in the same sense that a normal program would have only a single entry point because of backwards determinism. However, despite this, when we would specialize a reversible program, suddenly it might have multiple exits. This would be due to us reaching this exit state with multiple different static states. And one solution to handle this, which we took for now, was to simply make all these output variables that are changed dynamic. This is certainly a point of future work to improve. Secondly, when we do specialization, when we get to a conditional jump, we make the conservative choice of specializing both of the directions. However, when we have the come-froms here, there is no guarantee that we have specialized both of the directions that originate from it. And if we don't have both of them, then this is simply also just a syntactical issue. But we can't just remove it because we want to maintain the semantics of the original source program. Here, the assertion statement actually does the work for us. So we instead have an unconditional come from, which then adds an assertion to the body. But perhaps the most interesting one of all is this wonderful case where, let's say, we have one source block that is specialized to multiple different residual blocks, which means that it has multiple different static states encountered. However, there is a danger if they somehow all end up with the same output state, because that means that they will all point to this same block. But we only really allow for up to 2 blocks to point to the same subsequent block with this come from statement. And there's really no way to distinguish here where we came from. And this is actually just a massive issue with backwards determinism because, as I mentioned, this means that we all have the same static output state. Notably, this must then mean that we have performed some non-injective computation at the specialization time, which then means that we must not do that. One such issue could, for example, be if we have this simple block here, and we say that we have a static x initially and a dynamic y, and we add x to y, this is fine, but we then add y to x. Thereby, the current value of x now depends on the value of y, but y is dynamic, which means that the new x must be dynamic. So for example, we have the input state x is 3, y is dynamic, and the input state x is 5, y is dynamic. Both of them become the same output state, non-injective, horrible. The solution to this specific instance would then be, for example, a uniform binding time analysis, ensuring that all of the static elements only depend on other static elements. Yeah. And with that, we can actually begin talking about, once we've handled all of this and written a specializer for it, we can then begin specializing programs. Here we have a similar program to the first Fibonacci program. This is a partition program, which essentially we have an input list y's, and then we pop the first n elements of y's into another list x's. This is done in addition as another loop program. Interestingly enough, since we want to specialize here on the n, which is why it's blue, all of the forward jumps are actually static, which means that the final residual program will actually be a straight line program, and it will look kind of something like this. And then once we have this, we can do some post-processing, namely the transformations mentioned previously, and we will get, or actually, let me just say that we're specializing with n equals to 2, which means you can see that we have this loop body twice in the final residual program. And then we get this following output. This is the thing that our implementation will produce. However, I have highlighted 3 specific statements. These are some assertions. They were introduced by us wanting the well-formed come-from statements. But the annoying thing is the fact that if one carefully looks at the semantics of the program, it turns out that these are actually not needed at all. They're redundant. They will always be trivially true. But this requires some human reasoning to do for now. And here on the right-hand side would then be the truly optimal partition program with respect to n equals to 2. However, we have also done some interesting experiments. This one will take a bit of time to explain. So in a language RL, we have written a reversible Turing machine interpreter, this RTM-RL. And with that, we can take some input Turing machines, for example, the increment Turing machine here on top. And then, since this is a reversible Turing machine, we can also invert it, in addition to inverting the interpreter in RL. And these 2 different choices are then the 2 different paths here on the graph. And we can do partial evaluation on both of them. And the top path is simply just the first Futamura projection. We are specializing an interpreter with respect to an input program and getting a compiled version of that program. But the bottom path, more interestingly, we are actually specializing a program with respect to the inverted interpreter and thereby getting an inverted program. This is, I believe, called the first inversion projection. And while this graph is always semantically known to be true, the interesting thing for this to be a successful application for us is actually whether the final quality of the 2 increment programs produced by these 2 different graphs, if they're roughly the same. And by that, it's a bit of hand-waving thing, barring labeling of the different blocks, but the important thing is the runtime behavior of the amount of steps executed, etc. And we did this specific case, and we found that they were actually very similar. But in general, this is incredibly tough to reason about, mainly due to it depending on not only the partial evaluator, but also the specific interpreter you have written, in addition to the inverter for that for the language you're interpreting. But we have also done some more simple tests. For example, for quantitative results, we have here a few programs. Notably, we have the reverse Turing machine interpreter that we've specialized with multiple different kinds of programs. And we see that the size of the residual programs produced is, in general, a bit bigger. This is mainly due to partial evaluation. We often unroll loops. And for example, in the encryption program, we've really unrolled a loop. But interestingly enough, for the RTM example, we actually see that the residual size is more correlated with the size of the input program you give to the interpreter. But perhaps most importantly, we want to talk about the speed of things of these same programs. We actually find that here it's especially for the Turing machines that we get a large speed up to 6.5x. If we were to talk practically for the smaller cases, this speed up could also be vastly improved by this assertion removal. We had these redundant assertions introduced. They severely harm the speed up. But in conclusion of the things we've talked about today, we have done some partial evaluation in a new paradigm. We have done the first, as to my knowledge, successful application of the inversion projection. And we have identified a lot of future work, some of which I will be continuing to work on for my master's thesis. And I think that's about it. That was surprisingly fast.
questions?
A clarification point. This speed up was comparing which to which?
This is the speed up of the residual program compared to the original program with the same input. And we are doing speed up as in just the number of steps executed by these different programs.
So you decided that in pattern matching, the program should be linear in the pattern.
Yes.
Right? Is this a restriction that's very restrictive, right? You could, for instance, say that rather than using each variable exactly once, it could be at least once, and the program could perfectly well still be reversible. So is this a requirement that sort of is it strictly required to require linearity to decide whether or not the program is invertible, or is there some relaxed notion of linearity or relevance?
If one wants to have multiple variables, one can still just kind of, I mean, yeah, it's like the easy way to do it. The safe way is to have them be linear, because there's a bit of like unexpected semantics of the actual pattern matching going on, because we're not actually creating or destroying any values. We're merely moving them around. But if one wants to mention it multiple times while also, promising that it's reversible, then one could simply introduce a temporary variable and then copy the value over there, and then use that in the pattern matching. Yeah.
Okay, yeah, thank you.
Other questions? So maybe it's not directly related to your work, but who is the target user of your flowchart language?
I mean, right now, this was I would like to say purely theoretical, but I would also like to think that in general, partial evaluation of just any reversible language could be supremely useful, because there are many interesting reversible languages. Of course, quantum computing, I believe, needs to be reversible.
Yeah, sure.
And also, I believe that a reversible program has a lower minimum amount of energy needed to execute compared to an irreversible one, because some energy is needed to destroy information. And then that in mind, when also combined with partial evaluation, we now further reduce the amount of computation and thereby energy needed. So I'd like to think that for the future, this work will be very useful.
Mm-hmm. Sounds good.
In the speed up that you showed for the reversible Turing machine examples, was that which path was that based on in the graph that you showed? Are you reversing the Turing machine or the program, or the Turing machine or the Turing machine interpreter?
Here we are not actually reversing anything. This is a pure application of partial evaluation.
Just out of curiosity, you mentioned there's lots of future work, and some of which you'll address in your thesis work. So, what are your plans, basically?
Well, a lot of it is also we've developed a few hunches about what is possible. For example, when we get to these wonderful issues we've had, one of them is having all output variables be dynamic if they're ever changed. This is a very annoying thing. But also, in general, this also ties in with the fact that we have a uniform binding time analysis. I believe, spoilers, that it might be possible for it to become a point-wise binding time analysis, and therefore, with a bit of extra work, we might also be able to ensure that we only make the output variables dynamic at like the last possible moment, which is at exit point, and therefore maintaining the nice efficient computation from static variables until then. We even have I had a really nice program that had a really nice speed up until we realized this issue and we implemented it, and then it just became fully dynamic now. So I'm really annoyed by it, and I'm excited to see it actually work again.
Okay, thank you. Nice.
So, as a programmer, I sometimes like to validate to myself, sort of convince myself that my program is correct by writing, for instance, a little program that reduces some input to a Boolean. And but the cardinality of this code domain of my test function is very small, right? And so my unit test is maybe not reversible. Right? What are techniques for testing these reversible programs?
Yeah. So that is, of course, a very interesting thing. This injectivity can often be found to be very limiting. The way we often try to do it is we want to do things a very garbage-free way, which is we do not want to have some trace or some extra baggage along the way. But I haven't really thought of a nice way of testing these things other than just, calculating in your head and seeing the expected value at such and such. Yeah, I'm sorry.
All right, so it's maybe there will be a paper about RL unit.
Maybe, yeah.
All right.
Could you go back to the commuting diagram, please? So you said you observed that going either way, in those two paths, right?
Yes.
You got roughly approximate, did you systematically compare those two things? Now, here's the question, really. If you go through the bottom path, you basically seem to have a uniform translation, right, of the reversible Turing machine to to the reverse simulating Turing machine. That's a universal construction, and you keep the original program. And one would imagine that the top way is sort of like more refined or maybe faster, because you can use all kinds of tricks in taking the incremental, the Inc version, the application program, and are not limited to whatever the universal, the generic way of doing it through the bottom. So, question is it conceivable that there might be instances of programs instead of Inc RTM where you see a significant difference in the outputs, or not?
Yeah. So I actually think that this is also one of the things where this diagram is certainly only this nice theoretical commutativity in actually this case where we have the uniform binding time analysis and such, because then we maintain all of this static computation will only be done for all of it. For example, if we had the pointwise one where we do a lot of static computations and then it becomes dynamic, then in the inverse example, we will maybe immediately become dynamic and then miss out on all these nice static computations. And I think, but for this specific partial evaluator, I think even specifically the minor difference in the runtime performance we're going very down into the nitty-gritty, and it's also another thing I want to really focus on for my final thesis is the specific difference in these two programs, I believe, is actually caused by us specializing the normal program versus the reverse program, and like for the Turing machine essentially is just looping through all of its different rules, seeing which one match. And I believe that the difference right now is caused by it looping in two different directions, and therefore the order in which they match causes a difference in the amount of instructions executed.
So the answer was yes, you expect there to be a significant difference.
Certainly. But for this partial evaluator, yeah, still, yeah, even then.
Okay. So compared to other reversible imperative programming languages like Janus, then sort of execution order can be reversed at any time. Sort of time reversible, you can press pause and rewind the program. Right? Do you lose that property in RL?
That property is in essence it's backwards determinism. In Janus, which is also the language that Torben Mogens has partially evaluated earlier. I don't actually believe that you can actually reverse it at any point. It's more the fact that you have function calls where you can decide to uncall a certain function, therefore just running it in inverse. Right now we do not have functions in RL, so you can really only do forward execution, or you can invert the program and then do complete backwards execution.
Okay, and then this procedural reversibility, is that sort of fundamentally different from the way Janus is reversible, for instance?
I do not believe that there's anything really stopping us from implementing procedures. No, RL is designed to be very extendable, I'd like to say. You can extend it with a lot of different non-reversible operators even, as long as you can't use them in like the C-like plus equals assignment thing, etc., etc. There's a bunch of future work if anyone's interested in doing cool applications for domain-specific areas.
Thank you.
Okay, so let's thank the speaker again. Okay, our last speaker is Xu Lei, and he will be presenting a DSL for developing automated refactorings. Please start.
Okay, hello everyone. My name is Xu Lei Liu. Today I would like to introduce our ongoing work towards a language parametric DSL for refactoring. So refactoring is a hard problem. So manual refactoring is error-prone and time-consuming. To reduce time, we want to write automated refactorings, but writing them is still hard. So one key challenge is name binding. So why we say name binding is one key challenge? So let's look at an example first. So here, assume we have this program and we want to rename the X in class A. And if you want to do this, you also have to find all references to X in class A, right? For instance, like X in class B. So a correct renaming refactoring would only rename the reference this X to Y in method F. So why not rename the X in G? It's because if this X is resolved to X in class C. So finding the right references to rename is one of the name binding challenges in refactoring. But there's more to it. So we also need to take name capture into account. So for instance, if you insert the field Y in class B, right? So the previous renaming would not work as before. So why? It's because this Y, it will resolve to the Y in class B. So, but finally, we want this Y to resolve to Y in class A. So one solution is to add a super keyword here to let it resolve to the Y in class A. So name binding is not solely used in renaming refactoring. Manual refactoring is also need this name binding information. For instance, extract method, extract variable, an inline class, and a method push down as a method pull up. I didn't list all of them, but there are lots of kinds of refactorings. So this raises a question. So how do we write transformations that query and construct name binding? This is the question. And based on this question, we provide the following contributions. So we present an embedded DSL in Haskell for language parametric refactoring, and it has a couple of key features. First is name binding using scope graphs. Scope graph is a language parametric framework for name resolution. Based on it, our DSL provides integrated support for querying and updating name binding information. The second is ideas from strategic rewriting generic term traversals. Using generic term traversals can be specified concisely. So we borrowed a subset of generic term traversals from strategic rewriting. The third is transformations as patches. We enforce patch philosophy in our transformations. That is, its transformation can only change an AST node at most once. So now let's focus on the first key feature, name binding using scope graphs. So here is I want to introduce and illustrate how scope graphs enable us to query name binding information. So let's consider the program we used for renaming before. So here is the program. So in scope graph, at first you have the root scope SR, the scope of root, and it with a declaration for each class. For instance, A it represents the declaration for class A, and the B for class B, C for class C. Next, each class is associated with a scope in the graph. So here, A is associated scope is as A, scope of A, and the B as B, C as C. So these scopes are connected to root scope via lexical parent edges. So here is labeled P. So in this way, the declarations in the root scope are reachable from class scopes. So next, if a class extends if a class extends another class, so there is an extends edge from the extending class to the extended class. So here, for instance, here is a class B extends class A. So there is an edge from scope B to scope A, labeled E. Class scopes have declarations for fields, for instance, in B, int Y, and methods. But for simplicity, we only show the field declarations in the graph. Finally, each method also has its scope. So here in the case, function this method f, it has scope sf, and the function method g, it has scope sg. So how to resolve a variable in the scope graph? So to do this, to resolve variable in a scope, we start from the scope and construct a resolution path, follow the edges of the graph. So you can see if we have a variable x, okay, I think I can, okay, sorry. If we have x in scope f, so if we follow the resolution path, we will find that its declaration is x in scope A. So in this case, we know that x in scope f is resolved to x in scope A. But the x in scope A is reachable from x in scope G, but it's not visible. Why? Because there is a shorter resolution path from SG to SC to x in scope C. So in this case, this x in scope G is resolved to x in scope C. So now we know, so we find all the references that could be renamed. In this case is x in method f. So the next, if we want to rename x to y, this y should be resolved to the same declaration as before. So if we follow the resolution path, we will find the y in scope f is resolved to y in scope B. So yeah, this renaming is not correct. So our solution is to add a super keyword to it. So yeah, in this way. Okay. If you need to add a super keyword here, you want to let it find the correct reference. So this give you a flavor of how scope graph works. So next, I want to illustrate how our DSL supports the transformation and querying embedding information. So let us consider how to draw the renaming transformation in our DSL. So first, we start by using a generic traversal operator box to visit all AST nodes. So next, this box is parameterized by a function whose argument is a pointer to an annotated AST node. And this AN is a function that you give it a pointer to an annotated AST node, it will give you back the annotation of the AST node. Next, we can pattern match on the ASC node. For instance, if it's a field access node, yeah, we may want to rename it. But if it's not, we do nothing. This is the second case. 0 means we do nothing. And if we want to transform the field access ASC node, we can do it if and only if it references X in scope S. So how we do this? We do this by adding set conditions. So here TGT is a target. It means the target scope of the resolution path is S. And the name of this X1 is the same as X. So in this way, you guarantee that it references X in scope S. But if you want, before applying your transformation, you also have to check name capture issue. So how to do this? You can do this, for instance, if you want to rename X to Y, so you have to resolve this Y in the target scope again. So in this case, the resolve function will give you a resolution path. So the first is, if the relevant path is nothing, it means it doesn't find one valid resolution path. So it's very safe to rename. But if it's found one, and if the name would cause a name capture issue, so we will throw an error or name capture error. But if it's not, so okay. If it's not, we can also transform the program. So that's how our DSL works on this example. So here I want to emphasize how we enforce transformation as patches. Here is a patch function. So you give it a pointer, you give a pointer, and you give a pattern. So the patch function it will create a transformation for you. So in this way, we enforce transformations as patches. So in a patch, an AC node can be changed at most once. So since our work is an ongoing work, this is a short paper. So we have some tasks, still have some tasks to fulfill. The first is we have to do more refactoring case studies. So the second is we are considering transformations beyond refactoring, for instance, for compiler optimizations. And the third is to develop a standalone DSL with better error messages and ease of use. The reason is currently the DSL is embedded in Haskell, whose error messages could be improved and whose ease of use could be better. So to conclude, we present a DSL for language parametric refactoring. It has 3 key features. The first is name binding using scope graphs. Second is we borrow a subset of generic term traversals. And the third is transformations as patches. Yeah, that's it. Thank you.
Questions?
Thank you. This is wonderful. Since the early 20th century, fighting with capture avoiding substitution and getting the definitions right has been a hard problem. So the classical approach to is doing this with compilers, you have a static environment, you just carry around actually the pointers, environment to actually we're pointing to, and then you're building basically a dependency graph, right? But in terms of if you look at the classical literature, you're using saying like, oh, in case I get basically a non-capture avoiding substitution, I'll putting a super Y. The classical approach in logic would have been actually to rename not the free variable actually, but to rename the bound variables, because this will always work whether or not you can find the binding definition, binding occurrence of the variable or not. Why not do that? So in other words, why is that not good refactoring? Is whenever you see there is a binding occurrence in the way of renaming an applied occurrence somewhere else, you rename the binding occurrence, and of course, all the applied applications. If you know what I mean now, as like.
Yeah, no, but
so instead of writing super dot y, you would just write y, and replace the x or the y in the subclass by y prime.
Sorry.
So if you go back to the example.
Yeah. Yes.
Just look on the left, right?
Yeah,
So whenever you want to, you want to change X in class A to Y, you would go into class B and replace the Y by Y prime and all the applied occurrences.
Yeah. So at first, I'm not very familiar with the classical lectures.
Oh,
yeah,
okay.
So currently, what I'm doing is we wonder. So currently, our work is we would not how to say it. The choice is provided by the choice is given by users. Is how to rename this one. So it's another work developed by TU Delft students. So currently here we want to have a standard framework for finding this issue. It's how to fix this. It's another story. Yeah.
You may go ahead. Then,
So you may want to rename the bound occurrences. It really depends on what kind of refactoring you're doing, right? If you're refactoring a large code base, then and you're renaming things in your API, that may not be what you want. The framework lets you query this information. You can write this renaming transformation. It does not make decisions about whether you want to do this. It gives you access to all the information via the scope graph, which is really building on the same view as you have in classical compilers. Scope graphs are really just symbol tables. So you can do this other renaming transformation if that's what you want. Yeah.
Yes, okay. My question is related to the previous one. So, but in a sense, the graph you are building, it seems to me a little bit too complicated. So you have edges labeled by E, edges labeled by P, dashed edges, and then just too much information, I think. Are you sure that this is the minimal information you actually need to do this rewriting?
So
you have the source, the round thing. I mean, it's a bit too much for me. I would suggest a simpler graph, which actually you described in words when you said, oh, but this Y is related. Anytime you have int Y is related to Fritz's question. You have a binding there, so these are no called Y, they are Y primes. So you could represent this easy reasoning in a simpler graph. This is my view, but it's just, I'm not sure.
Okay, so
maybe to the last question. Oh, okay.
Do you want to respond? Okay, I'll respond. I'm not sure I see exactly how the graph would look alternatively. It is so the graph contains basically all of the binding information that you need to type check the program. And it may be a bit too much for some purposes, but it may be just what you want for other ones. So we're not making decisions about exactly, we're not trying to abstract too much. We're providing all of the name binding information that is in the program. We're trying to preserve all of it so that you can write transformations that you use all of this information. It may be that there are simpler ways of doing it, which are maybe suitable for other purposes, but yeah, I think that's an interesting question. I'd be curious to hear your thoughts.
Yeah, I think so. So basically, we derive this information from type checker. So I think, yeah, in the future, you can also simplify it based on your own needs. Yeah.
I think we should stop here and have lunch. So thank you. just this. Yeah.
Welcome back, everyone, to the first session after the lunch of PEPM. And it's my pleasure to introduce Tuki Tsuyama, and he's going to talk about algebraic effect handlers.
So, hello everyone. I'm Tuki Tsuyama from Tokyo Institute of Technology. I will talk about an intrinsic type compiler for algebraic effect handlers. In this work, our goal is to develop type-preserving compiler for source language with first-class continuations. We focus on type preservation property rather than efficiency. Previous work developed type-preserving compilers for various source language features. And we consider manipulating first-class continuations and developed a type-preserving compiler for effect handlers. We selected effect handlers as a source language facility because it is practical and can express various effects by manipulating continuations. We prove type preservation by implementing an intrinsically typed compiler using the dependently typed language Agda. Pickard et al. Developed the intrinsically typed compiler for language with exceptions. We extended it for effect handlers. Intrinsically typed compiler converts between intrinsically typed AST, which only represents well-typed terms of implemented language. The advantage of intrinsically typed compiler is that type-checked definition can be regarded as proof of the type preservation of compilation. Intrinsically typed AST is designed to represent well-typed terms, but not to represent ill-typed terms. Let's look at simple AST in the Burnett language. It can construct ill-typed terms such as 1 plus 2. And this is the intrinsically typed AST of Burnett language. Data type exp receives the additional parameters of data type tie for types of Burnett. This AST cannot construct ill-typed terms like 1 plus 2. The main challenge of this work is typing continuations to ensure the safety of continuation manipulation. In the previous exception language, continuations can be only discarded. But in our source language with effect handlers, continuations can be captured and resumed. So we cannot use previous typing as it is. To solve this challenge, we incorporate a stack polymorphism for typing continuations in the target language. This technique originally proposed by Morissette et al. But we argue that the key novelty of our work is using stack polymorphism for compilation of manipulating continuations. Let us begin by looking at how effect handlers in the source language behave. Our source language is the simple language with effect handlers. Effect handlers are the generalization of exceptions and handlers. In this language, operations causes effect, and handlers determine the behavior of operations. Handler can freely use continuations bound to K. When this program is executed, the operation OP is called, and the process moves on to the corresponding computation in the handler. In this handler, continuation is resumed with by the value 0. In the resumed continuation, the operation call is replaced by 0. Now, handler computation finished with returning the result value 1. Then, the return clause is executed. It returns given value as it is, so the final result is 1. Now let's see the detail of our work. First, we define the intrinsically typed AST of source language. Value and comp and handle are the data types representing well-typed values, computations, and handlers of source language. Value is annotated by value by values typed CTX and VTI representing the typing context and type of values. And comp and handle types are similar. Next, I explain our target language. Our target language is a set of instructions to the stack-based machine. Now, let's see how effector handlers is emulated in target language. I show the stack transitions resulting from the execution of the compile source term. First, the compile handler hand is pushed onto the stack. The entity of hand is a collection of compiled clauses. The execution moves to the handled computation. This computation pushes one onto the stack at first. And next, the operation OP is called. When capturing the continuation, the stack used by the continuation is cut off and bound to K together with the continuation body. Now execution moves to the operation clause. This first pushes K and 0 onto the stack. Next, the continuation resumed. At this time, stack is reconstructed by the stack stored on K. Then further execution follows, but I omit to explain. Now we know how to execute effect handlers in target language. Now let's see the typing in target language. Target instructions are typed by typing context for variables and two stack types before and after the execution. When typing resumable continuation in this method, the challenge arises. The challenge is that the input and output stack is not known when capturing continuation. For example, let's look at two cases for continuation resumption numbered 1 and 2. The shape of the stack when executing the continuation body depends on the context in which the continuation is resumed. We solve this challenge by incorporating stack polymorphism to our target language. The type of continuation body quantifies the stack at resumption large S2 and the output stack large S3. By doing this, unknown stacks at capturing can be abstracted. Finally, let's see our compiler. Compile function is the intrinsically typed compiler for top-level program of source language. The type signature of compile represents the statement of typing preservation. So we can regard type-checked definition as proof of type preservation. We define the compiler function with some auxiliary functions and type-checked all definitions. So we could prove type preservation. All implementations can be found on the GitHub linked in our paper. Our future work is to prove semantic preservation properly. We think this can be achieved by extending compiler calculation method used by Picard et al. And then we are interested in type preserving compiler for other continuation facilities, such as shift 0 reset 0, shallow handlers, and so on. Finally, we are making type preserving optimization compilers based on continuation usage. To achieve this, we plan to extend the source language with the notion of multiplicities, which represent how many times variables is used. So, in the summary, in this work, we implemented an intrinsically typed compiler for effect handlers. We incorporated stack polymorphism for typing continuation. As future work, we plan to prove semantic preservation. investigate other continuation facilities and making type-preserving optimization compiler based on continuation usage. So this is the end of my presentations. Thank you for listening.
Do you have any questions?
Thank you for the talk. Could you please show the type preservation function signature that you had on the slides earlier? So from, no, sorry, this was, yeah, this exactly this compile. So from this, it looks to me, therefore, that the types of values which you can store on the stack in the stack machine is the same as the types of values that you allow in the high-level language?
Yes.
Yeah, so did you think about having a stack machine which was more low-level, so the and you would have to do a type transformation? Because I would be surprised to see a real stack machine where you can represent all high-level values on the stack, right?
So what do you mean by simpler?
Sorry?
What do you mean by simpler?
Like, as in, like, so I mean, so I'd expect, for example, this A on the left to be possibly some compound high-level type.
Mm-hmm.
And I would expect for a stack machine, the individual stack value, do you allow for the individual stack values to also be large compound types? Would you expect them possibly to be simpler types, like, for example, just primitives? And then you would have to express that you do some sort of mapping for a compound into primitives, or?
That might be possible. We are just following previous work on intrinsically typed compiler for exceptions, and they're using this kind of typing.
Okay, so they're also doing this. Okay, so okay, this wasn't a decision that you made. Okay, so thank you.
Can you comment on this intrinsic types? Are they essential, or they just make your proof easier?
Yeah, the advantage of intrinsically typed compiler is it's describing how to compile, how to perform type preserving compilers with implementations and type preserving proof at the same time.
Okay. Also, can you comment on how do you deal with the bindings in your formal proof, and how much like boilerplate code proofs do you have for dealing with the bindings?
Yeah, we use for the Brown index for variable bindings. So yes, that's because the some previous work use it to implement intrinsically typed AST. So it's easy to use for to implement our AST.
Do you have any other questions? I've got one more question. So you said one of the basically future work things is to have also kind of show the preservation of semantics. Do you already have an idea how you would go about this with the compiler calculation?
Yes. Compiler calculation is a method to derive compilers satisfying the semantic preservation. So in concrete, and this method derives by equational reasoning, starting from the equation representing the semantic preservation. So it uses the definition of AST and source language AST and definition of interpreter.
Okay, thank you. Thank you. Otherwise, then let's thank the speaker again.
That we should probably wait a little bit because it might synchronize with.
Yeah, but do you really want to wait 7 minutes?
Yeah.
I think that might be a bit.
So I'll be up to you to decide.
Yeah, but 7 minutes, I don't think that's. Okay, then our next speaker is Izumi Tanaka from the University of Tokyo, and he's going to talk about ownership types for verification.
Okay, hello, I'm Izumi Tanaka from the University of Tokyo. We propose a fully automatic verification method for imperative programs with pointer arithmetic. Here's an example of a target program, which includes pointer arithmetic and assertion, like this. The verification goal is to check the lack of assertion failures in this kind of program containing pointer arithmetic. Our method is an extension of the approach of consort proposed by Thoman et al., which combines refinement types and fractional ownership types. This is an outline of the rest of this talk. First, let me review the idea of consort. A consort is an automated verification tool for imperative programs with mutable references, but without pointer arithmetic. As I said, it is based on a type system combining refinement types and fractional ownership types. Let's see through examples how to use ownership types to handle mutable references. This program creates x as a reference to 0, creates an alias y for x, and then updates the value of x to 1. The assertion on the last line fails because x was updated to 1. The value of y has also been updated to 1. If we naively apply refinement types, we may perform the following wrong reasoning. First, on the first line, x is given this type, and which means that x is a reference to an integer 0. On the second line, y is given the same type. A problem occurs on the third line. As x is updated to 1, we are tempted to change only the type of x to this one, meaning that x is now a reference to the integer 1, and leaves the type of y as it is. But that is wrong because y is actually an alias of x, so the type of y should also be updated. In fact, with this type of y, we will wrongly conclude that the assertion on the last line will succeed. To address this issue, a consort combines fractional ownerships with refinement types. Here, we have added ownership 1 and 0 to the types of x and y. 1 represents the full ownership for the difference, so x can freely read or update it. On the other hand, 0 represents no ownership, so the refinement type of y on the third line cannot be trusted. Hence, we cannot wrongly conclude that the value of y is 0. This is a slight variation of the previous example, where the value of y is now asserted to be 1. And the alias information, this, which tells the type system a hint that y is an alias of x. Thanks to the alias information, the type system of consort can redistribute a part of the ownership of x to y. 1 is divided to 0.5 and 0.5. And propagate refinement type information to y. Now, since we have information that the value of y is 1, we can conclude that the assertion on the last line will succeed. Let me summarize the notion of fractional ownerships in consort. An ownership is a real number between 0 and 1, which is assigned to each reference type. When aliases are created, we maintain the invariant that the sum of ownerships for the aliases is at most 1. The ownership 1 represents the full access to a reference, so that the refinement type can be updated. 0 means no ownership, so the refinement type information cannot be trusted. And an intermediate value between 0 and 1 means that refinement can be trusted, but cannot be updated. Now, let me explain our extension to handle pointer arithmetic. In consort, as I've explained, a reference type represents the ownership and refinement type information for the cell pointed to by the reference. In the presence of pointer arithmetic, however, we need to let a pointer have ownerships for memory cells around the cell referred to by the pointer, not just for the single cell at P. For example, for this expression to be valid, P should have an ownership for the cell pointed to by P plus 1 instead of P itself. So we extend the syntax of types like this. This is the type of integers that satisfy phi. For example, this type is a type of integer 3, and this type is type of positive integer. And this is the type of pointer where tau describes the type of the value stored at P plus I. In this figure, the value P0 has a type this, where the index I in tau is substituted by 0. And the value P1 has a type this, where the index I in tau is substituted by 1. And here, R, called an ownership function, is a function that takes an index I and returns the ownership for the cell at P plus I. In this figure, the pointer P has ownership 0 on the cell referred to by P and has an ownership R1 on the next cell. Let's take a look at examples. This is the type of pointer which refers to the head of an array of length 10. Here, this expression is a shorthand for this function. And this is the type of pointer which refers to the head of an array with first element 0. And this is the type of pointer which refers to the second cell of the array. Here, a refinement describes the value in the cell which is one cell before, the one referred to by the pointer. And this ownership function has ownerships from index -1 to 8. And this is the type of pointer which refers to the head of an array with 0 in the first half and 1 in the second half. Let's take a look at typing example. This function, named init, takes an integer x and a pointer p as arguments and initializes 0 to x minus 1 values of p with 0. First, p has no refinement information. First, this program checks if the length x is positive or not and assigns 0 to head of p. Then the program makes a new pointer q and recursively call init function. Finally, elements from index 0 to index x minus 1 are initialized with 0. Now let's take a look at the typing of this program. The type of function is this. Before a function call, p has no refinement information and has ownership of the cells from p0 to px minus 1, like this figure. And after the function call, p's refinement is changed to this new equals 0. And let's take a look at the function body. When assigning 0 to p, the refinement is updated like this. The value of the cell referred to by p is updated to 0. Next, with the pointer addition, ownership of p is divided like this. P has an ownership only at index 0, and q has ownerships from index 0 to index x minus 2. This figure shows q has now no refinement information. Next, when calling init function recursively, the type of p its argument q changes based on the type of the function. Now, all elements of q are initialized with the value 0 like this. Finally, ownerships are redistributed based on this area's information. Here, ownerships are gathered to p. As a result, the type of p matches the function type after the call. Next, I will introduce the formalization of our type system. A type judgment is formed like this. This gamma is type environment, and this data is the function type environment. This type judgment means that the expression E is well typed under theta and gamma, and the expression E evaluates to a value of type tau, and the gamma describes ownerships and refinement types before the execution of E, and gamma prime describes those after the execution. For example, before execution, X has full ownership from their index 0 to 4, and after executing let Y equal X, ownerships are divided into Y. Consequently, X has half ownerships from index 0 to 4. Here's an example of typing rules. This is rule for assignment. For this assignment to be valid, P must have a pointer type as described in this type environment. and P must have the full ownership 1 as described by this premise R0 equal 1. After the assignment, the type of the value stored at P is updated to tau P prime. Here, this condition says that the value of P0 is now n, and this condition says that the values of the other cell remains unchanged. Next, let me explain our type inference procedure, which serves as an automated verification procedure. This is an overview of our type inference process. The overall flow of the inference process is the same as consult. But please note that the second step of ownership inference is much more challenging because we have introduced ownership functions. In fact, this part is one of the main contributions of our work. So I'll focus on explaining this part in the inference process. The outline of the type inference process is as follows. First, we do simple type inference like this. Next, the ownership function at each program point is inferred by ownership inference. Finally, we infer refinement like this. Ownership inference is done in these steps. First, for each program point, we prepare templates of ownership type environments and introducing variables representing unknown ownership functions. Now our goal in this process is to infer these functions. Next, we generate constraints on the function variables based on the typing rules. For example, on the first line, P must have full ownership at index 0 due to the assignment of 0 to the head of P. Then this constraint is generated. And on the second line, we generate this constraint because ownerships are divided through pointer addition. We then solve the constraints collected from the entire program. However, these constraints on function variables cannot be effectively solved by off-the-shelf SMT solvers. To address this issue, we restrict the shape of ownership function to this form. Here, the value of ownerships are represented by W, and boundaries of cells with the ownership value are expressed by linear expressions of integer variables in the program. We prepare variables that represent this unknown ownership value W, as well as unknown coefficients C and D. Based on that, we can reduce the constraints on function variables to constraints on variables W and Ci and Di. In our example, the resulting constraint is this. This constraint is changed to this, and this is changed to this. And now our goal in this process is to infer these number constraints W and C and D. Unfortunately, however, the resulting constraints still cannot be effectively solved by off-the-shelf SMT solvers because the constraint involves nested quantifier like this. So we iteratively approximate this formula to this in a counterexample guided manner, where the universal quantified formula is replaced by the conjunction of formulas obtained by instantiating variables x to several concrete values. And this concludes the ownership inference, and the next step is refinement inference. And this process is almost the same as consult. First, a template is prepared at each program point, And here, Schüler X is variables in program. Subsequently, constraints are generated based on the typing rules. And these constraints are in the form of constraint horn clauses. And we use CH solver to solve them. If refinements can be inferred, then we can say the type inference is successful. Next, I'll explain our experiments. We implemented an automated verification tool. The input of our tool is a program with no annotation, which means no type annotation, no ownership annotation, and no alias annotation. The output of the tool is safe or unknown. If the tool successfully types a program, we can say the program is safe. Conversely, if the tool cannot type a program, we can only say the safety of the program is unknown. We conducted verification on some benchmarks prepared for our experiments. And this is the result. We compared our tool with an existing verification tool, C-Horn, which is a CHC-based automatic verifier for C. As you can see from the result, we successfully inferred ownerships and refinement for these programs. In other words, we can verify the safety of these programs. Let me introduce a benchmark program. This is SumDeep, a summation function. We divide the array into two halves here, P and Q, like this. I recursively call the summation function in each here and here. Then return the sum of them. In the main program, we prepare an array initialized with non-negative values and assert the sum of values in the array is no less than 0. Our tool could verify this program. Let me explain related work. There are some free automated verification methods for pointer manipulating programs. However, these methods do not work well in the presence of pointer arithmetic. In fact, they not effectively handle our benchmark. Additionally, there are some semi-automated verification condition generation approaches to pointer manipulating programs. These approaches cover a wider range of pointer operations such as XOR, but require heavy human interventions like annotation of loop invariant and pre or post condition for recursive function. And this is the summary of this presentation and our future work. Thank you.
Thank you for your talk. Do you have any questions?
Thank you for the talk. It was very cool. I really liked it. I was interested about, so the you mentioned that you had to take this approach for approximating the solutions for your inference equations to because you couldn't use an off-the-shelf SMT solver. So is it sort of correct to say that you are sort of restricted in the pointer arithmetic that you can approximate here? So here you're doing addition, but are you restricted that you can't do many other operations, or can you?
Sorry, I couldn't understand. Please, once more.
Sorry. I'm curious. So here you mentioned that you have to use this approximation approach. I wonder if this approximation approach restricts the kind of pointer arithmetic that is now possible on the sort of formulae that you have. So you said you restricted the shape of the formulae to be the shape with the variables that you showed. So does this mean that you can't do pointer arithmetic with XOR now in the future at all? Or other functions, for example? I would like to know.
Actually, we didn't think about other operation like XOR. So now I can't say clearly, but
yeah. Yeah, so certainly the restriction on the shape of ownership functions has to do with the fact that we cannot deal with XOR. Yeah, because now we only allow ownership functions where so we only allow a pointer that has ownership for a contiguous memory region. But in the case of XOR, you have to ownership for some more in a more general form. Okay. And by the way, so the approximation on the phase C does not have to do with our restriction on pointer operations. That's just a kind of trick to solve the nested quantified constraints.
Hi, thanks for the talk. So regarding your experiments, did you try out or find any benchmark that cannot be handled by your approach?
Yes. Okay. We we conducted experiment on some these simple examples only.
Okay.
So
I see. Okay. Yeah. Thanks.
Hello. Thanks for a very good talk. What I was curious about is, do you have any examples where you separate the ownership and then put it back together, maybe like in the quicksort function, where you divide it into two arrays, sort, and then put it back together?
A sort function.
Yeah.
To handle sort function is
Okay. Okay, thank you.
So nested pointers is kind of a well-known challenge for any kind of ownership analysis. Can you say a little bit more about your plan on that? Nested pointers.
Nested pointers.
Yes. Well, so it's a well-known challenge for ownership analysis. Can you say a little bit more about that? What do you plan to do, and what are the challenges you foresee?
About future work?
Yes.
Okay. We can actually our type system can handle nested pointers, but now our tool cannot. For because our tool is now prototype.
It's just a matter of implementation, not self-application.
I'll ask a quick question if that's okay. Which CHC solver did you use?
We use spacer and voice.
Other than I've got a question. So I was curious about what's the inference rule like for conditionals. So in your examples, all the conditionals basically had one trivial case, like one of the branches was basically a base case. But what happens if you have kind of complex branches, basically both do something interesting? How do you then type the conditional?
Branch?
So you gave one example for an inference rule for your type inference, right? And I was just curious what the type inference rules for conditional looks like, because I can kind of guess what it is for if one of the branches is more or less does nothing, like it's a base case and nothing interesting happens. But what does the rule for the conditional look like, the type inference rule? If you can sketch that on a
conditional. No.
So just the idea, how do you merge these types? Sorry?
It's just like a Woodland rule for refinement type system.
Just the, yeah. So you can basically have complex operations on both branches. That's not a problem. Yeah. Okay, then if we don't have any other questions, then let's thank the speaker again. And the next talk will be remote in a few minutes, 10 to 3. So how does it work now with the remote? The next one is remote. I think so. Yes. Yeah. We'll next talk. No, that's remote. The next one is remote. Do you have the speaker already?
Someone has logged out from the space, so I might need something.
Okay.
Hey, so how are you doing? So where are you going to be this evening? Congratulations on that. Good excuse. No, I don't know what to do. Yes. I'll just ask her right away. Maybe call. Rolling up. He was wearing
Okay, so Fritz, the sessions. So we managed to sort out all technical problems, hopefully, and we have Guillaume online, and he's going to give a talk on scoped and type staging by evaluation. Go ahead, Guillaume.
Okay, hi. Sorry, everyone, I couldn't be down in London with you, but the teaching term started yesterday. Yeah, so this started as an attempt to understand András Kovács' work on two-level type theory and how to use it to do stage compilation. So this was, I'm hearing some echo, so let me stop this. Okay. Right, and to do this, what I did is that I opened ACTA and I started doing my favorite thing, which is to formalize languages in a scoped and typed way, and then trying to see how the staging and the two-level go up. So the goal here is to have a language in which we can do generic or meta programming in a way that is we are able to use at least the same language, maybe even a richer language. It should be type safe. I don't want to have type errors at code generation time. And it should be with no abstraction cost whatsoever, which is a usual problem when we use like a universe of descriptions, for instance, to do our generic programming in. So let's start with a quick example. So here I'm defining the diagonal of a circuit. First, we have this gadget. Let's just ignore all of the indices, but what the type of DOP is saying is that we have a term of circuit type with one input and two outputs. And you can see the circuit on the right-hand side here. It's implemented using a MEX combinator, but it doesn't really matter for this talk. And then we have this function here called diag, which will take a circuit that has two inputs and one output and return a circuit with one input and one output. Again, there's a lot of noise with quotes and splices and so on, but we can just ignore them for now. And the idea of this combinator is that we grab the circuit that's passed as an input, and then we form the circuit that first takes the one input, duplicates it, and feeds it to the gate. And this is implemented on the left-hand side using a lambda, and then quotes and splices and sequential composition and so on. And then finally, we can use this diagonal function to describe the NOT gate as the diagonal of the more fundamental NAND gate. So this mentions a lot of like function application, lambda abstractions, the Brown variables, etc., even though the language of circuit doesn't have these kind of facilities. So luckily for us, the staging will get rid of all of the higher order aspects of the language, and then we'll end up with a proper circuit. So not at the bottom right here, we can see that it will partially evaluate to what we expect, the sequential composition of duplication and the use of the NAND gates. So then let's see how we can implement this in ACTA. So I'll try to give a quick refresher of scoped and typed syntax and semantics, and then how we can patch it to have a minimal two-level type theory. So let's start with simple types. For the simply typed lambda calculus, we have a base type, alpha, and then we have a type of functions from A to B, which are also two types. So in this presentation, and generally I find it easier to never mention the ambient scope, go back to Martin Love style inference rules, where we assume there's an ambient gamma, we never talk about it, we only talk about the adjustments we're doing to it. So on the left-hand side here, you can see we're threading gamma everywhere, but on the right-hand side, we have equivalent rules where we only mentioning in the bottom right that we extend the current gamma with a fresh variable of type A when we go under a binder. So to do this sort of stuff, we have a bunch of combinators I'm not going to introduce. You can read about them in the paper, but I will show them. I will show you how we can write these types now. So you can ignore the for all and the fat arrow, etc. These are the combinators that are doing all of the threadings. But morally, what you see is that on the left-hand side, we have a constructor whose type is, if I have a variable of type A, then I can build a term of type A. And on the right-hand side, you would have the corresponding inference rules. So if we have an application, it's a similar process. If we have a function, well, a term for a function of type A to B, and a term for an argument of type A, then we can get a term for a value of type B. And on the right-hand side, you have the corresponding inference rule. And finally, the last piece of the puzzle to get the simply typed lambda calculus is lambda abstraction. And here there's a bit of noise again from the encoding, but you can see that apart from the noise, the rules look a lot the same again. So on the left, you have the constructor for lambda abstraction. If I can build a term of type B in an environment extended with an A, this is the same as being able to build a term of type A arrow B. And so when we put all of this together, we have this really compact definition of what it means to have a well-typed and well-scoped language. And then we can write our first example. It's a very boring one, I'm sorry, but it's just the identity function from A to A. And here we just use a lambda abstraction and then use the variable immediately. So this is in the Brown syntax. I didn't give the definition of var, but you get the feeling it's just going to be 0 and successor, basically. So once we have this, one thing we're typically interested in is defining a normalization function for it. And a really nice way to do this is to go via model construction, an intuitionistic model construction. So the first key ingredient in building such a model to get one of, right, so we build this model so that we can write this evaluation function. So this evaluation function tells us that if we have an environment assigning to every variable in gamma a value in delta, then provided that we have a term in with variables ranging in gamma, we can produce a value with variables ranging in delta. Right. So the first key ingredient in designing such a notion of value, in building such a model, is to have Kripke function spaces. So for this, again, we have some really nice syntax that encapsulates the idea of Kripke function spaces. So here you can see it's defined as the box of a function space between two predicates of a context. The box is inspired by modal logic, and it's telling you that something is true in every possible extension of the current context. So a Kripke function space between P and Q is something that will, in any possible extension of the ambient context, give you a function from P to Q in that world, basically. And then ignoring, again, the noise from the syntax, etc., the important thing to see is that on the right-hand side here, we have this double lambda thing, which is a way to say that we have a semantic notion of lambda that allows us to build Kripke function spaces. And then the next definition gives us the double dollar, which is like a semantic notion of application, stating that if we have a Kripke function space, then we can actually use it in the current world and actually get a proper function space in the current world. So once we have this, we can build the model by induction on the types that we're interested in. The value of type, the base type, will just be a term at that type. In principle, we could enforce that this is a normal form, but in this talk in particular, we're not really interested in about normalization, just about evaluation. So I'll stick with just term. And then the value of type A to B is interpreted as a Kripke function space from values of type A to values of type B. So this is a standard model construction, intuitionistic model construction for the simplified microcosm. Then I mentioned earlier environment, telling you there were mappings from variables to values. This is what this record definition is saying. And then the important thing to know about environment, apart from the fact that we can look up the value associated to a variable, is that we can extend an environment. And this is we have this very generic type of extend saying that if you have an environment for variables in gamma at the current ambient type, then in any, in the current ambient context, then in any extension of the context, if you get a value in that extension, then you can build an environment for variables in gamma extended with A, living in that extended context too. So what this is saying is that basically we can always embed the current environment into a larger context and also throw in extra values. Once we have all of these elements, we can build the evaluation function. And it is now purely structural because we've introduced the right notions. So you can see that a variable gets interpreted as a lookup in the environment. A syntactic application becomes a semantic application where the subterms have been evaluated recursively. And then a syntactic lambda becomes a semantic lambda where we recursively evaluate the body in the current environment extended with the value that was just given to us by the semantic lambda. So this is the standard definition of this modern model construction. And now what we want to do is extend the language with two-level features and also get a new model construction that will accommodate this extra expressivity. So let's look at a minimal intrinsically typed two-level type theory. So the idea behind this two-level type theory is to be able to clearly state what should be present at the static level and will be evaluated away during compilation, during staging, and what is purely dynamic and will stay behind. So here we have a silly program that applies the identity, but a dynamic identity, to an argument which is built using a static identity applied to the dynamic identity. And then what we want to have after staging is that all of the static parts go away and we end up with just an application of the dynamic identity to the dynamic identity. So to make all of this formal, we need to say what the different stages are. You can ignore the phase argument here. It's a purely technical matter that's discussed in the paper so that we can have a precise notion of normal forms. But so here we define two stages. We have the static stage, which will go away during staging, and we have the dynamic stage, which will be the code that remains after we've partially evaluated our programs. And then we have our notion of types. So our base type is available both in the static stage and the dynamic stage. And then one thing that András remarked is that our function types need to be homogeneous in the stage they live in. So this is what really makes it work. And it's enforced here by saying that they can be at any stage, but it needs to be the same stage that's used for the domain, the codomain, and also the overall type of the functions. And then we have this strange gadget of quoted types. So you can think of it as code. So it takes a dynamic type and it gives you a static type corresponding to the programs that are going to eventually evaluate to a program with the dynamic type that's associated to it. Once we have our stages and types, we can give the definition of our language, again, in intrinsically typed and well-scoped way. So this time we can once again ignore the phase annotation and mostly the stage 2, except for the last 2 cases. So first we start with the same constructors as for the simply typed lambda calculus. We have the variable, we have application of a function to its argument to get a value, and then we have lambda abstraction. All of these, because we are building a minimal 2-level type theory where we have the same features available in the static and the dynamic phase, are fully polymorphic about the stage they can live in. But then we have 2 new constructs. We have quote, which turns a dynamic term of type A into a static term of type code of A. This is the trivial notion of a program that will eventually produce a dynamic term of type A. It's basically just embedding one that's already there. And then we have splice, which allows us to take one of these codes for dynamic program of type A and turn it into an actual dynamic program of type A. And so that's where some computation will happen during staging. And this is all we need to have a very minimal 2-level type theory with staging. So now that we have the syntax, we need to also extend the semantics so that we can actually residualize these programs to get purely dynamic programs. So our goal is once again to write an evaluation function that will, provided an environment and a static and a term, return a value. So this time our notion of value, because it is indexed by the stage, will be defined by case analysis on the stage. So the value for static terms will be defined by an auxiliary definition called static, but the value for dynamic terms will be purely syntactic terms, because we want to partially evaluate away all of the static parts and end up with proper terms for the dynamic parts. And then you have the static definition below, where the static terms of type base type are just the empty type. That's because we don't have any constructors for our base type. If you had, say, the natural numbers, then you would have a bit more structure here. You would have actual natural numbers as the static values. The static values of type code for an A is actually a dynamic value of type A, which is to say just a term of type A. And finally, the static functions from A to B are the Kripke function spaces from static values of A to static values of B. And we can once again define the evaluation function. It's purely structural. Let's just ignore the few first cases for var, app, and lam for now. We can focus on the quote and the splice, and you can see that in the model, they're just the identity. Their meaning is just the identity. And then this is what is really interesting, is the meaning of app, of application, will depend on the stage. So application in the static stage, remember that these static values are actually computing, so the functions are become Kripke function spaces, and so we use the semantic application for Kripke function spaces here. But the application for dynamic terms, because they're purely syntactic, will become the purely syntactic app constructor from the term family. And it's the same for lambdas. The static lambdas become Kripke lambdas, semantic lambdas, and then the dynamic lambdas are purely syntactic objects. We don't really care about the arguments passed to B here. So the take-home message is that the model construction for the staging of this 2-level type theory is a mix of the normalization by evaluation model construction we use for the standard STLC for the static parts of the language. And then for the dynamic part of the language, this is basically the usual definition of substitution. This is the action that we see in substitution. So this gives us a minimal 2-level type theory, but of course what we'd like to do in practice is have something with a bit more features. So one throwaway comment in Andreas's paper is that the meta language can actually have a lot more features than the object language that we end up with after staging. And so in the paper, I have an example of a radically different meta and object language, where the meta language is this fully fledged functional language that I showed earlier, and then the object language is purely circuits. And so here you have an example of the sort of things you can do this way. It's maybe a bit scary, but you have the diagram below describing what it does. It takes a function from a Boolean to a very simple circuit with one output and one input, and turns it into a circuit with two inputs and one output. And the second input is basically a control signal telling you whether the function should be applied to true or false. And so this is effectively a generic tabulating gadget that will turn any function into a circuit. And it's defined purely in these things. Okay, so what next? Well, one interesting thing we could do is try to prove the soundness and completeness of the staging using a logical relation. I expect this is just deploying standard techniques. We could have a dependent type circuit description language. So the problem with the tabulation function I showed you earlier is that it's for circuits with a set inputs, set number of inputs and a set number of outputs. But of course, we maybe like to have a generic definition of tabulation instead. It would be nice when we want to have the exact same language at both levels to just get a description of the standard functional language and then automatically lift it to a two-level construction. Everything is very, has the same structure, so it should be possible to write this generically. And finally, I showed you that quote and splice had a very boring meaning in the model. They were both the identity, and it would be nicer to have computationally interesting quotes and splice. So I've already found two, which are again dealing with circuits and functions from bit vectors, but it might be interesting, maybe some of you have ideas in mind of cases where you could actually have interesting quotes and splices that would actually have a computational content. Thank you.
Thank you, Guillaume. We have time for a few quick questions.
Hi, Guillaume. This is Sam Lindley. Thanks for a very nice talk. This is very pretty. Had you considered extending this to multiple stages?
No, I haven't, but this is a feature in Andreas's original paper where basically you can have an index, you can have an infinite tower of stages, and then every partial evaluation stage will lower the whole language by one step. So I imagine this would be doable. Yeah.
And with heterogeneous languages, so different languages at each stage, do you think that would work?
Right. I mean, the construction is fairly generic in the usage of the stages so you have a single family, but because of the indexing, you can ensure that some constructs are only available at certain stages. So you could definitely do this with more than two also.
Thanks.
Do you have any other questions?
Just one comment, but I think you have a first stage in which you deal with the semantics, the cryptic function spaces, and the second, which is syntactic. So I think your approach is more applicable to the two-level cases, because otherwise you have to have a lot of semantics levels. Do you agree?
Well, so I think that you would basically define in parallel potentially semantics for each one of the layers, and every time just shaving off the top one while staying purely syntactic in the older ones below?
Okay, then thank you again. And now, Yu Kong, give the last talk in this session before we have then our last session on the history of PEPM.
Where's my slide?
Is it?
I don't see my slides.
Is it on a different screen? Oh, something? Yeah.
Okay. All right. Thank you. Hi, I'm Yu. I'm trying to define a one-pass CPS translation for dependently typed languages, and this talk is a short report on my progress so far. So I'm doing this as a step toward dependent type preserving compilation. So a compiler is said to be type preserving if it translates a well-typed source program into a well-typed target program. And this property is particularly important when the source and target are both dependently typed, because preserving dependent types would mean preserving various program invariants such as positiveness of numbers and sortedness of lists. In the literature, we have some results about dependent type preserving CPS translation. And the latest work by Bowman et al. Shows how to translate the sigma type using naive CPS translation. And this work aims to extend Bowman et al.'s results to a one-pass translation. A one-pass CPS translation does not yield any administrative redexes, so the translated program runs faster and is easier to reason about. And I'm going to show you what kind of new challenge will arise in defining such a translation. Okay, so as a warm-up, let us quickly review the naive call-by-name CPS translation in the simply typed setting. So suppose we have a source term second of E, where E has a simple product type. The CPS translation of this term looks like this. So it takes in a continuation K and applies the CPS of E to a continuation that takes the second element of the received value V and resumes with continuation K. And it is easy to see that this translation is type preserving. In particular, the types of the continuations required by and passed to the second of V are exactly the same. Now we do the same translation with dependent types. So suppose the source term E has a dependent product type. In this case, the whole term has a type that depends on the first of E. The CPS translation is the same as before, but this time the result is not well typed. We see that the type of second of V depends on the first of V, whereas the type of the continuation K depends on the translation of first of E. These terms are syntactically different, but it turns out that there is a way to prove that they are in fact equivalent. The intuition is that if the source term E is a pure term, that is, if E has no control effects, then the continuation passed to the translation of E will receive the unique value. This unique value corresponds to the result of evaluating E, and it can be extracted by running the CPS of E with the identity continuation. And using this fact, we can show that first of V is equivalent to the translation of first of E. Now the question is, how can we formalize this intuition so that we can use it in the type preservation proof? The solution of Bowman et al. Is threefold. First, we make the answer type of the translation polymorphic. That is, we add a type abstraction in the top level translation. And this guarantees that we can always extract the value of a CPS term in a type-safe manner. And second, we define a new typing rule for the target language. This new typing rule applies to application of a CPS term to a continuation, and it allows us to type check the body E2 of the continuation with the knowledge that the received argument V is a specific value. And this gives us the first two equations here. And thirdly, we add a new equivalence rule to the target language. This rule says running a CPS term E with a continuation K is equivalent to first running E with the identity continuation and then passing the result to K. This property is sometimes called naturality, and it gives us the last equation here. So using these techniques, Bowman et al. Were able to prove type preservation for their CPS translation for sigma and pi types. Great. So my goal is to prove the same property for a 1+ CPS translation. As I said earlier, a 1+ translation does not yield any administrative redexes. And one way of defining such a translation is to use a column translation, which takes in a source term and a target continuation as arguments. It is called column because the separator is usually written as a column, but here I'm using bar to avoid confusion with the typing relation. So, as with the naive translation, 1+ translation is easy with simple types, but when we have dependent types, we need to, again, solve the type mismatch when typing the body of the continuation. So let's see if we can apply Bowman et al.'s techniques to solve this type mismatch. The first step is to make the answer type polymorphic. This works well. It allows us to extract the value of E. And the second step is to define a new typing rule. And then we realize that this typing rule is not useful in our context. The reason is that a 1+ translation does not yield applications of a CPS term to a continuation. So now the question is, how can we use the knowledge about the unique value received by continuations? My current proposal is to use something that I call a definition lambda. A definition lambda is a variation of lambda that has a definition representing what value will be passed to the function. Its typing rule uses the definition to derive the body and also concludes with a type that also refers to the definition. The idea behind this definition lambda is actually not new. There is work on ANF translation of dependent types, and they use similar typing for contexts. But interestingly, this definition lambda poses a new challenge in 1+ translation. So if we use a definition arrow type to define the top-level translation of types, then the translation of a source type A would refer to the source term E, which inhabits the source type A. This seems to suggest that we need to translate terms and types in parallel, and that would complicate the type preservation proof of the translation. So that's basically my results so far. I believe that it is possible to define a 1-pass CPS translation for sigma type, and I hope to report some positive results in the near future. Thank you.
Thank you, Yu. Do you have questions? Got a few minutes.
This would be very nice if you can make it work. I got a bit confused by what a definition lambda is. It looked a bit like a let binding to me.
Yes, yes.
Is
it
it
a
different?
Function. Yes.
How is it different from a let?
So in CPS translation, you need to represent continuation using as a function, right? Instead of a let. In ANF translation, it's fine to use let.
Okay. Well, I look forward to seeing the final version of this.
Thank you.
Very pretty talk. Is there any way of using, like, it seems like you've got these sigma types and you actually know what the left-hand side of the value of the sigma is, right? The first component of the pair. So maybe you could make that manifest in the type instead. So you have a sigma type where you know where you record in the type what the witness is. And then maybe that gives you more information. It'd be a bit like your let, like you've got this function type that records in the domain what the witness is.
That's an interesting idea. Yeah.
Or maybe you could use singleton types in the target language, and that could be used to define these definition lambdas, I think.
Yeah, that's also possible.
Yeah, thanks for the nice talk. And it seems that one naive approach to the problem is to use Bowman et al.'s CPS transformation and then to reduce the administrative rejects if Bowman et al.'s target language type system has a subject rejection. Yeah, I'm wondering it works or why it doesn't work. Then why? Yeah.
Yeah, it would probably work. So the target language of Bowman et al. They did not prove type soundness, but just a translation to some known calculus. But I think, so for simply typed languages, we have this 1-pass translation, and I would like to know if it's also possible for dependent typed language.
So more direct correspondence to the.
Yeah.
Yeah, thanks.
More questions? Otherwise, I think we're done right in time for coffee. Thank you again.
Thank you.
definitely does that. Decimator definitely does that. Strip
Yeah, so it's probably still working. Do you want to just double check that it's working?
Okay, cool.
It's
there. It's there.
Oh, okay. Door was open. So welcome to the final session of PEPM 2024. Maybe the final session of PEPM, no, hopefully not. I have a very privileged position here. So my name is Fritz, and I'm the session chair, but I'll spend a lot of time introducing the session to you, because in part because our first speaker, Dines Bjørne, couldn't make it for the presentation, which is actually his privilege, you could say, neither here nor online. So what is this session about? So this session is both looking backwards, but in reality also looking forward. So it's about the history of PEPM. Many of you actually, some of you maybe are not even old enough to have been born when PEPM and some of the work was conceived of and started. So to give you a little bit of an idea of actually the history of this quite long-running sequence of workshops and symposia. And this has been worked jointly with some colleagues here, but I'll be very careful to point out that I've taken the privilege of exploiting that I had to prepare this today with very few, I shouldn't even say plural hours. So I'll take this as a privilege to make this a rather subjective and a little bit hasty reflections, and hopefully to also engage you. It's late, 1600 hours, and so you're welcome to comment. Some of you have been there, and some of you will give actually your own presentations later on, which are all keynotes and invited presentations. So just to set the stage, so what is this is a very short history of PEPM. It's even shorter than the book's called A Short History of. So 1971 is like a critical year. Yoshihiko Futamura published a paper where he described something called partial evaluation and showed that you can represent programs and then write interpreters, and the programs are data, and then you can apply them. And if you have a certain kind of program that partially evaluates one of two inputs, in the sense that it only evaluates actually, but does something really actively with the first input, and the second input is basically symbolic, doesn't have it yet, then you can arrive at some fascinating, actually, in principle, results, namely that you can have an interpreter and turn that one into, partial evaluator, turn that from the partial evaluator, turn that into a compiler, and actually then turn the interpreter via the compiler to compiler generator, in principle. So this was a paper kind of work. So then Valentin Turchin and Andrei Yershov in back then the Soviet Union, were aware of this work and worked on their own framework for doing this, mostly in a context of a functional programming language, Refal, which is really a language for symbolic evaluation, you could say, and very aggressively having ideas how you can actually perform, this kind of what they call mixed computation, computing with, you get a program, but then computing with static values, real data, and some other data basically being symbolic, they're not available yet. So, and then in 89, and 85 to 89, we've had this work at DICO, led by Neil Jones. And I'll spice what I'm saying here with a couple of very, some kind of anecdotes. Later on, hopefully we'll get to hear more anecdotes. So I was in 87 to 89, I was at NYU and working in the programming languages group there, working on Settle 2, and type systems for that. And then, one of the PIs, Ed Schoenberg, came in and said, it's like, he's just seen this work. Some crazy people in Copenhagen trying to make Futamura's original idea work in practice, okay? So he thought this was so exciting and crazy at the same time that we should actually read some of those papers. It's the first time I heard about this. Little did I know that for other reasons, I would end up in 1990, 91 at the very DICO Institute. But it was my introduction basically to the work on partial evaluation. So a critical part in this one was, and Dines Bjørne, you gotta look at his and read his very anecdotal presentation of actually how it came about, how he had visited the Soviet Union and met with Andrei Yershov. I talked to, of course, Neil Jones, and he's the co-organizer of this PEMC, Partial Evaluation and Mixed Computation workshop. Well, have a picture at the end. I hope I have a picture at the end. And organized this in 1987, pulling together, actually for the first time, bringing together physically Futamura, Yershov, I think Turchin was there, lots of other people that you know will be were there. For example, Lisp 5 1.5. Yeah, sorry. John McCarthy and various other people who are very interested in basically symbolic computation and the partial evaluation here. So this is basically, sometimes you might think of it as the title of his article, the zeroth PEPM, you could say, but it gathered the community and caused a lot of excitement. So a lot of excitement came from the fact that actually it was in principle possible, and then you could make it work. There's some new ideas that came out of this one, like binding time analysis, so this was actually then the basis for the series called Partial Evaluation and Semantics-Based Program Manipulation is actually the full name, so abbreviated to PEPM. And over the 3 decades, it has broadened focus. Namely, it's focused basically always on the idea of programs as data objects and their semantics respecting, I would say, processing. Okay, so it's basically data. So the focus is on data. Let's do something with the data, but make sure that we don't just screw it up, like, I don't know, by just, doing something that might be correct or not, but the focus being on both being, creating efficiency, but being semantics preserving. Now, so why a PEPM history celebration? As you know, every time people who celebrate history might be worried about their future, maybe should be, but the original forum. So PEPM has been, I would argue strongly, has been an original forum for great ideas. Okay, so did they arise at PEPM? Probably not, but they were exchanged in a forum at PEPM, and then later on actually kind of dissipated into, like staged, computation. I didn't mention it here. So partial evaluation, practice, staged computation. We've seen some of it is, and general forms of constant propagation. They're so widespread and mightily used. You could say that they've moved into other, have moved out and moved into other applications, industrial applications, but also conferences. Okay, so there's a couple of these things, as you can see, and these are in boldface because you will get historically minded and intentionally personal, I hope. We encourage to make them as personal as possible. Introductions with a historical view and a personal view on partial evaluation by Peter Sistoft, and on program transformation by Alberto Petrossi, and on program incrementalization by Annie Liu, who is unfortunately not here, but hopefully you're out there and giving us an online presentation. So more than 10 years have passed since the 20-year PEPM reflections, which were actually also performed, and actually one of the motivations that maybe not so implicit as you can imagine are the following: the field's founders are not getting younger. Okay, so Yoshihiko Futamura, he's very much alive, but was very interested and was very, very actually excited about the project here, but his health is in no state right now, and he sends his best regards to actually contribute in writing or even he doesn't have a voice anymore, basically. So he's not. Andrei Yershov just passed away some time ago. Valentin Turchin also some years ago. Neil Jones, who was actually expected, when we started with this one, we expected to get a written contribution. His voice was not very good. He unfortunately passed away last year in March 2023. So which just highlights why we're trying to get some of the classics, you could say, on the record in this context. Andrei Klimov, not to be confused with another Klimov in Russia. So he's basically an exponent of the Yershov Turchin school from old. He was very much interested, but he could not contribute due to illness, right? So he's in the hospital still, as far as I know. And Dines Bjørne, he's, if anybody who knows Dines, most of you know his son, Nikolai Bjørne, but Dines, his father, and anybody who's worked in Denmark knows he's been a force of academia, a force of industry, and in general, a force of nature. So I can only tell you this now, Dines is not getting younger. I think he's 84. He walks on 2 sticks. But when he retired, so people forewarned, there's anecdotes here. When he retired, his retirement lecture was not a lecture. It was a 5-day, so a whole week of retirement lectures, all of them given by, Dines. So Dines is unfortunate here. I would have loved you to actually see Dines in action here, because he's literally a force of nature. So, get out of the way when he came. Now, anyway, but he's really unfortunate here right now. But so we have his record, especially in his unusual style of presenting actually a background of how he traveled around the Soviet Union and tried to get to visit places he was not allowed to be visiting when he was there, and so on. So read about this. So the last part we try to do is the following: is we try to encourage the founders and key contributors to loosen the reins of stringent academic, whatever you want to write here, academic, restrictions, okay? So you just have to say, like, oh, I don't know, where's the novelty and all these things and significance. Put a very personal touch on it. So this was actually an explicit charge, people have solved it in different ways, but an explicit charge is like, you're not only allowed to, you're required to put your very personal touch on reflecting on the field that you've been a founder of, okay? And the last 20, 30 years doing this one. So saying like, please do actually contribute anecdotes, okay? Please do contribute personal reflections, and in particular on the interplay of academic cultures, personal idiosyncrasies, and motivations behind what you and we usually read in the papers, because that's just the final. It's like watching a movie. It doesn't really tell you how it came about, right? So, and we'll get some great stories from all the invited contributions later on, right after this extremely long introduction. So, so the history of the PEPM history celebration is so long it has a history itself. So we talked about it some time ago. So in POPL'22, the starting point was having invited keynotes by key contributors to the field, you could say in general, but also present at PEPM. So we had talks by Naoki, who's unfortunately not here, Andrei Klimov, as I mentioned, Frank Fenning, who's also been a huge contributor to many of these things, by Peter and Annie Liu. So the idea was then, let's solicit written contributions, okay, written contributions that are not ephemeral and disappear and dissipate into our memories, so other people can read them later on also, with a focus on the early years, okay? So you can imagine also, because maybe they're the older ones, so it's more important, or quite important to get those. So PEPM'23 was actually intended to be the one, but then we still had COVID, and POPL was in the US again, so I think it surprised a couple of us, because we thought we'd start here in the US, and then, next year then, have a European PEPM, as usually very often the case. So that's the reason we decided to actually then do it this year. And despite late invitations, mea culpa, we had enthusiastic responses, okay? So as I said before, there was actually a resounding positive response, but not everybody could respond. So the title actually of this talk was updated by Ming to also say something about Neil, because Neil Jones, he's unfortunately passed away last March, and this was actually quite rapid. So when I talked to his wife Line, who I know very well, she pointed out that his laptop, a Mac, was open, and he was in the middle of a terminal session where you could see that he was actually working on some kind of self-applicable interpreter. Okay, so he worked on a couple of things, like not only that, but he was very actively working with people and some of the potential collaborators. He's written paper as late as 2023, right? It's published. So he was very much engaged in this one. And then sadly, it was open on the date where he went to the hospital and never came back. So there's a remembrance. It's only 2 pages. Read it. I think it gives an idea of actually, with titles, what Neil has done in his career, because many people know him for this or for that. So the complexity theoreticians are computability people. They will know him for truth table reductions or p-completeness, or areas in complexity theory, or the first sort of solution to the characterization of the spectrum problem for finite model theory. And many of us here maybe will say, what, really? We know him for partial evaluation, for program analysis, for binding time analysis, for data flow analysis, for semantics-based compiler generation, and all that kind of work. Okay, so but what Neil actually managed to do, and it was rather unique, and it's actually a dangerous thing to do. So for you, the young people amongst you, don't do that. It's a career breaker. is actually working not only across doing this and doing that, but actually transporting ideas from programming languages and programming into complexity theory to get new tools for dealing with complexity classes, characterizing them, and showing actually some refined complexity class hierarchies and so on, and taking ideas from computability and complexity theory and putting them into the programming language world, very often by what's called implicit complexity theory, which means like, looking at complexity theory as maybe some kind of way of capturing closure properties by formal languages, classes of languages. And very often you will find out there's lots of people interested in this one, lots of people interested in that one, and very few that actually in the middle there. Well, he managed actually this in a very unique sense. So please read this, because I can't do any justice, but I just want to show you a quote from Neil's Neil Fest, which we had when he retired. 2007, he organized a retirement seminar. It was not 5 days, don't worry about it, single day. And we had to talk Neil into it. He was like, oh, don't make a big deal out of it. In general, Neil was the kind of person, don't make a big deal out of it, so he would be yelling at me right now. So he wrote in his presentation himself that he gave, which was entitled 45 Years of Research and Teaching, he wrote in one of those statements in the beginning, it's like, hey, I made a great discovery in the beginning. I could go into these universities. He grew up in his father was a welder, and his mother was a housewife in the middle of America, literally in the middle of America. He would usually say, I grew up in the middle, no, wait a minute, exactly in the middle of America, okay? So he would say, wow, in a small town where he raided the library, but I could actually do what I enjoyed and even get paid for it, okay? So this was one of those things. So actually, it's a picture of actually where he's giving presentation at DICO. And one of the things that he would also highlight is the many publications he caused, okay? And he pointed also out one of them where he was actually top of the line. If you can't see it here, that's the front page, or it's a headline page in the main newspaper in La Réunion, an island, a French island in the Indian Ocean, right? Where they wrote up there, it's not impossible to walk, basically about a crazy guy who walked up the volcano in ordinary street shoes, okay? And if you've seen the shoes, that's exactly what Neil always had on. And of course, he took him up to the peak of the mountain. Great, so some reminiscences. I just want to, whoa. So just show a couple of pictures, of the field and the people. This is Yoshihiko Futamura, an early picture, I couldn't really find much, of Andrzej Yershov. This is Neil Jones, of course, and this was a Dachstuhl seminar. I think some of you were there, right? So, and that's actually Valentin Turchin. That's a grad student from back then, from Stanford, and there's Neil Jones and Yoshihiko Futamura, okay. So they met for this Dachstuhl seminar, which was also one of the rallying points for partial evaluation. Sorry. Some other, this was from Neil Fest again, so you can see Torben Mogensen here, with actually mustache, doesn't have that anymore. And Olivier Danvy, who's now in Singapore, who's been actually a major mover together with Charles Concel in establishing PEPM in 1991, okay? And in general, actually been very active, so it's in Singapore now. Here we have Neil and Alan Mycroft. Alan Mycroft retired recently, so this is when he'd realize luckily other people get old, not only ones, other people only get old, not other people. But you can see here a couple of people here also, like not only Morten Heine Sørensen, who was wrote very interesting papers, but he was already in a state, I guess, that reflected, it was a really great party, okay. Back there we have Patrick Cusot, okay. And in here we have Muli Sagiv, okay. And I think this is Pavel Urzicin, okay. So, Paul, this is, we had a great time. So I wasn't planning on saying all of this at all until recently, so, but I'd like to actually emphasize here, before we go, maybe at the end of the session, to flip our heads towards the future, okay, is looking at, thanks to the PEPM History Federation collaborators, we've worked on this one. So we have Zina Ariola, who's unfortunately not here. She's on sabbatical in Boston, couldn't make it. Sam, who's here. There we go, Sam. Hey. And Yuyo, of course, who's here, right? And we had, and their students, grad students who helped Zach at Oregon, and Yudai at Tokyo, and Frank, I think at, that was Edinburgh then, right? Yeah. And we also got some materials contributions. We solicited some of it. We expected to get 50, but we got 2. Julia Lawal, who provided some missing proceedings, the PEPM 99 proceedings. Thank you very much, Julia. And Neil Jones, who sent actually a picture of the PMC meeting, which is also in Dines's presentation. Okay, so you can look it up, and it also says who's present. So look in the proceedings, Dines Bjarna's presentation. That's it. So there's a very long session introduction. So to do justice, I'll actually do a proper introduction now of the first talk, and hope that's okay. I'll just move on to this one right away. Now, in the style of being very personal here, Peter has been a great acquaintance, I think, for everybody. So Peter has worked early on, and you'll tell us about this, how you got into this one, partial evaluation. But you've also worked on a number of other topics in programming languages, in spreadsheets, formalized spreadsheets, written a number of very important books that all can be characterized as follows. Is like, it takes only 80 pages to say it, or maybe 50, and really everything you need to know is in there, okay? So what are people spending 800 pages on if textbooks like Java Precisely or F# Precisely and various of these other books you've written. With that in mind, and Peter is also actually been doing, of course, important work in service of the community, but also at ITU. He's the department chair of computer science, served on evaluation committees at the Danish National Research Council, which I heard you said was not a lot of work, right? No, just kidding. So, floor is yours, Peter.
If I can use this one, yeah, we just want to get of course this behaves differently from when I tested it. So we just need to mirror it. Yes, yeah.
Or just slide it to the side, I think.
Probably, possibly. Or maybe some other direction.
Yeah,
yes, good. Right. Yes, so thanks a lot, Fritz, for the introduction. So I'm Peter Sestoft, and the paper in the proceedings is written together with Harald Søndergaard, who plays a big role in what I'll talk about now. But he emigrated to Australia 37 years ago, and it's quite a distance to London. The most important person in the history is Neil Deaton Jones, who Fritz already introduced. So let's see, this thing is a little in the way. So what I'll talk about here is, and Fritz almost did this already, prehistory, so that's before I came into it. Then what happened at DQ, the department, CS department at University of Copenhagen in the 70s and 80s, and then a description of the department, and then talk specifically about partial evaluation, where Neil and Harl and I come into the work with some personal recollection, so I hope you will bear with that. So partial evaluation probably doesn't need much introduction, but just to underscore what Fritz said, that this was sort of given a name actually already in the 60s, but what Futamura did in 71, apart from giving this equation, was to propose the Futamura projections, at least the first two of them, where specializing an interpreter with respect to a program gives a compiled program, a target program, and specializing a specializer with respect to an interpreter gives a compiler. And later on, when he was at Harvard, he added the third Futamura projection. Specializing a specializer with respect to itself produces a compiler generator. And early work in the 70s on this was mostly in the Soviet Union, in Moscow and Novosibirsk. Turchin and people in Moscow, Yashov and others in Novosibirsk, and people in Linköping, not so far from Copenhagen, worked on partial evaluation. But until 83, nobody had made a non-trivial realization of these the self-application that's involved in the second and third Futamura projection. So before I talk about what happened after 83, I'll talk a little bit about the CS department at the University of Copenhagen, where I myself am educated, and also a bunch of you guys here are actually from there. So, because Harl and I thought when you wrote the paper that this actually played a role in how this came to be. The department is established in 70 by Peter Nauer, and Peter Nauer had detailed plans for everything. So there's a little book called Plans and Ideas for the Computer Science Department, roughly 100 pages about how everything should be done in the department. Student project activity was core to his vision for this. So there's also a paper in an Italian conference about this. So the project activity has been core to this all the time. And then there was a new Danish university law from 70 also, and that's a coincidence. I think Nauer would not like, actually didn't like this law, but it has very strong focus on decentralization and democracy. So the so-called department council consisted of all faculty plus making up half the council, and 25% administrative workers and 25% students, and everybody had a voting right there. And at DQ even, and that was unique, in 1 year, a student was elected department head. A unique case. It worked really well, but there was a newspaper article about it, so it was strange even by the standards of the time.
And they changed the law?
Yeah. Later in 2003, the law was made much more corporate and professional, and you are welcome to put quotes on these terms if you want. So we don't work under this any longer. As department head, I can be sort of emperor in the modern system. So continuing about the department, it was housed in an old factory, not a university building, but it was very cozy and impractical. There was a student-run cafeteria where you basically put money in a box when you took something, and hopefully you would pay, but it seemed to work. There was lots of student teaching assistants in courses, primarily I think for lack of faculty, but also to provide ample feedback on those student projects. And one of the things that now are built into the program was so-called bedømmertimer, student peer review. So when a student had made a project or a group of students, other students had to assess this project and give a preliminary assessment, maybe not grades. There was also the first instance of a musical or specs revue. The first instance in the science faculty was at DICU, an annual event making fun of teachers' rules, the ministry, sort of really an anti-authoritarian thing, co-produced between students and faculty, and it's still running. And the result of all this was that there were tons of informal connections between different student cohorts. So I started at university in '81, and Mads Toft 2 years before, but I couldn't know him because of all of these informal interactions, and lots of interactions between students and faculty. So, and here starts the PEPM relevant part. So this is just a very short sort of overview of this. The first important thing is that Neil joins the DICU faculty in '82. And I was an undergraduate student at the time, and so I was subjected in fall of '83 to this. Neil wrote some lecture notes about functions, expressions, programming languages, and computability, covering a huge amount of things in 100 pages here. Including what will be relevant later, recursive systems of equations, compilation and interpretation and stuff. I really loved this stuff. It was so neat and compact and clear. Lisp was used as a meta-language everywhere, but Neil, like many sensible people, found that Lisp wasn't perfect, so we defined an extension with static Lisp-scoped let bindings and pattern decomposition, calling letlisp, and a preprocessor for that written in letlisp, of course, to turn it into Lisp. And all of the entire setup was totally wonderful. Then, in fall of '83, Neil heard about partial evaluation from Andrei Yashev, possibly at the IFEP conference in Paris, and also that self-application, the second and third Futamura protections, hadn't been realized. Independently, I think Niels Andersen, an associate professor in the department, held a seminar course called Automatic Programming. And Harald Søndergaard, one of the co-authors of this paper, was actually, according to the schedule for this course, presented Yashev's '82 TCS paper, which I think maybe Niels Andersen discovered independently of all the other things. And Neil and Harold got together trying to realize a self-applicable mix, actually in a sense as a student project. Neil didn't have a group at the time, he didn't have any funding, and also had to sort of work with volunteers. And the hope was to be ready for POPL a few months later, but it turned out to be too difficult to make a self-application work. And so I was totally unaware of this until what I think is a January afternoon in '84. I encountered Mads Toft discussing this really exciting idea of writing a specializer in the first place, which seemed crazy, and then applying it to itself to achieve compilation and so on. So I learned about it there. At the same time, or soon after, I'm not completely sure about the dates, Mads Rosendahl and Torben Mogensen work on a mix for a Pascal-like language with Lisp data. Somehow I managed to gate crash Harald and Niels' collaboration. I wonder how I dared do that, but maybe because of a short power distance in the department. And so we started working on this, and had really a lot of unsuccessful attempts on the way, which I'll specify a little more later. Somehow, during the summer or fall '84, we managed, by inventing a bunch of things, annotations, binding time analysis, and other things, and succeeded with this. In the beginning, call unfolding was controlled manually by annotations on calls, but then later, maybe '85, we managed to automate that as well. And I have very few documents from the time giving precise dates of anything. I've thrown away all papers from that time. So here are quotes from a couple of those student reports, project reports. That Harl wrote a report published in November 84 that says that during the autumn of 84, a far more successful approach has been elaborated by Neil Jones and Peter Sestoft, but this is false. It's Harold being too modest, of course. He was part of that. Also, Dybkjær writes the year after, it's the summer of 84, a self-applicable one, and Mogensen in his thesis in 86 says late 84. So it's sometimes in 84 we managed to realize non-trivial self-application, and therefore the second and third Futamura projections. And then we grabbed the nearest conference deadline and submitted a paper to Rewriting Techniques and Applications, May 85. So there's a draft of the paper from January 85. So we must have succeeded before December, I think, and wrote this paper and submitted it, and it was accepted for this conference in Dijon. Rewriting Techniques and Applications is sort of relevant, but not sort of, well, I think this paper is maybe considered relevant for this conference, but not sort of core, but it's the most cited paper from that instance of the conference. Okay, so taking a breath and a step, look back, why did we succeed in doing this? So I think there are at least 4 aspects to that. One is the design of the language handled by Mix. That's extremely important. The language that Mix is processing must also be the language in which it's written, if it's to be self-applicable. So the language should be simple to handle, but powerful enough to express conveniently a partial evaluator. So that's the same as, I think Turchin had this metaphor of an airplane engine. It must be lightweight to be lifted by the plane, but it must be strong enough to lift the plane. So that's why designing the language was not trivial, actually. Couldn't just take a Pascal or whatever was a full Lisp that was around at the time. Using Lisp data was core, and that you saw Neil use those in the computer science notes for the third-year program, third-year course, and that was a really good idea. There was an earlier attempt, which I'll show, that was too simple for experimentation, and then we came up with a somewhat stronger core language, L, to be handled by Mix, and the same idea of a preprocessor translating an extended version of this language into the core language. So we were primed for these ideas by Neil's work on the course, for instance, and his general approach to things. And I'll show the here's the early 84 subject language. So in an attempt to make the language as simple as possible, it actually didn't. It had only one syntactic category, expressions, and it had a program had one unnamed function, which had one unnamed parameter, and recursive call was executing with this recursion expression. So this language was really simple, and here's a self-interpreter written in a let extended version of this language. So this has you can bind variables and so on, and there's a preprocessor translating that into this. A self-interpreter is interesting because any good partial evaluator will have to be able to evaluate stuff. So somehow it must be an extension of a self-interpreter. And so that's a good thing to start writing in your subject language. But this turned out to be too cumbersome to work with. Even though you can encode everything in one parameter using Lisp cons, and then take it apart using car and CUDA and so on, this was too cumbersome to work with. And self-application wasn't realized there. Later, maybe in the summer, we decided that this language was too simple and switched to one that was slightly more complex. It's still a very small subset of Lisp, side effect free. But now it has multiple named functions. So a program is a list of function definitions, and each function has multiple named parameters. So a function definition is a function and a list of parameters and an expression. And here's a self-interpreter in this language. It's twice as long as the other one, but this was manageable. And just the convenience of having names for things was extremely important for experimentation, because we needed to make a lot of experiments to get anywhere. Actually, switching from the early 84 language to the late one, with multiple functions, multiple named functions, made program point specialization possible. And that wasn't possible in the first one without tons of encoding. And this is a super important way and convenient way of specializing programs. And most of the specializers written at DECO later were of this sort. This approach to partial evaluation was invented at the same time by Mikhail Polyonkov in Novosibirsk. Then we introduced annotation of operations, I'll get back to that, and binding time analysis and binding time improvements. So let's see if I can explain this. So the problem after getting a good enough language to work with was how to decide what to do with data. So when we have an expression like car of cons of xy, and x has value 2, should this be reduced to 2 or left as a residual expression? So reduce or not reduce. Or function calls, should they be unfolded or inlined or left as a function call where we know that x is 2 and z is car of w or something. These decisions can be taken online, and that was the standard until then, that the partial evaluator, the running mix, had enough information to decide, well, this was the best approach or that, but based on the values of x, y, and z, and perhaps other things. But at least we weren't clever enough to write a self-applicable mix in this approach. So applying online decisions mix to itself proved too difficult, producing either trivial programs that was just basically the given program with a constant added at the beginning, like Kleene's proof of the SMN theorem, or it produced large or even infinite residual programs. Something looping was the standard thing. And I recall, as I write also in the paper, in one of these many experiments over the summer and fall, I started a self-application computation on the PDP, the VAX computer we had just got at the department. Went to lunch, and when I came back from lunch, I was an angry computer operator because my program, which I'd written to disk, had filled all the remaining disk space in the entire department. So that's probably a very large program had resulted, but not an infinite one, because an infinite one wouldn't have terminated. So, so the idea was to let annotation decide. And I think this is typical Neil approach to things. Let's see, here's some problem that is impossible to handle. We don't understand it, but what if we help this partial evaluator a bit, and then we'll figure out later how to make this help automatic. So the idea was to decorate operations with S for static and D for dynamic, and then one can have car S of cons S, and then that will reduce to 2 if X is 2, but if you have car D applied to cons D, then you get the entire expression instead, and maybe the value substituted in here, 2 and 5. And then we have a 2-level language was invented here, and that made self-application possible, and I'll try to explain why in a moment. Because of first thing was that this was cheating, because we were helping the computer too much. So of course we wanted to automate this, and so we invented binding time analysis. And this wasn't foreign to Neil at all either. He had been working with explicit binding times previously. But we wrote this simple analysis that can compute the binding time of values, and then automatically annotate the operations using these computed binding time values. Function call annotation, as I said, was a separate problem. So the question is why this actually works. I think we didn't totally understand it at the time, but here's an attempt to reconstruct what works. By introducing a binding time analysis as a pre-step to partial evaluation, we actually give a mix an extra parameter. So in addition to the program to specialize and the data, the partial data to the program, we give it a binding time description, and then a separate stage. The annotate can analyze the given program and the binding time description, maybe SD saying the first argument is static and the second is dynamic, and produce an annotated residual, an annotated program to be specialized. And then the specializer proper will work on this annotated program. That's exactly how our mix came to work. And then there are some specialized equations for this. So with a 3-argument mix, the Fujimura projections look slightly different. So specializing an interpreter with respect to a program, we also need to give it a binding time description, SD, telling a mix that the interpreter's first argument is there, namely the program, but the second argument, namely the program's input, is not there. Compiler generation is a question of specializing this mix, given only the interpreter but not the program. So we actually have 2 arguments here. We have the interpreter and its binding time description. And therefore this mix being specialized as the input description, static, dynamic, because we have the interpreter, we have the binding time description, but we don't have the program. And so this is what makes a difference. And specializing, in this case, specializing this mix with respect to itself, but not the interpreter, means specializing. So this is this one, and this mixes this one, and this one is the binding time description. So we specialize this mix with respect to itself and the binding time description, but not the interpreter and its binding time description. And compiler generation and so on works on, again, on a tuple of the interpreter and the binding time description, or a tuple of the partial evaluator and its binding time description. And I think that is the important part, that this binding time description from the interpreter is preserved when we specialize the mix with respect to the interpreter, and this binding time description from the mix is preserved when we specialize mix with respect to itself. Because it tells us that the compiler being created here by mix should expect a program marked by S as input, but not the program's input, which is marked D. And so the compiler has a lot, so this mix this mix is being partially evaluated by this one, and this one has a lot more information at hand when making decisions on how to transform the interpreter during partial evaluation. So we get a compiler that works like a normal compiler. It takes a program as input, but not the program's data. Without this, basically mix would be obliged to produce a compiler that could also take the program's input as argument and produce a residual program. Then, when given the program, we'll run it on the data, which is not what we expect to get, and a much more complicated object. In reality, we didn't work with 3-argument mix, but with annotated programs, but the equations are exactly the same, and the important part is the annotation on the interpreter and on the mix given as argument there. Function call annotation, function call unfolding decisions were first made manually by writing an annotation on the call expressions. And then later we found a relatively complex way of doing this. Looking back, it's super simple, but I found it very complex at the time. Unfold a call if there's a static argument that does structural descent in its argument and everything else is equals. And later we found out it was actually much simpler to unfold a call if it's under static control, if and only if. And then if you look at the appendix of the Jones-Kumar-Sestoft book from '93, the specializer shown there uses this simpler approach. I think one reason we didn't invent the simpler approach is that even our late '84 language didn't have let bindings, proper let bindings, and therefore function calls also had the role of, if you had a very expensive computation, you wanted to do it once and use it twice, you needed a function call there. And therefore call unfolding should also avoid duplicating code and computations. If our language had let bindings, this extra restriction could be ignored, and I think we would probably have invented the simpler solution earlier. So even our late '84 language is actually a little too simplistic, I think. Adding a let binding to this language wouldn't make it much more complex, and would make the compiler from that to this simpler, and we would have understood call unfolding better, I think. And if you look back at Torben Mogensen's '86 master's thesis, he actually does have a let binding in his language. So I think Torben understood this better than we did at the time. Which you typically find that Torben understands everything better in retrospect. So good. What happened afterwards was this workshop that Fritz already mentioned in Fyn, with participants from all over the place. Chairs and editors was, of course, Neil, André Jaschow, and Tinus Bjørner, and he was sort of the moving power there. And here's a color photo. It's probably difficult to see from anywhere, but Neil is in the middle here. Turchin, John McCarthy, John Hughes from now in Gothenburg, Andrei Jaschow, Futamura, Tinus Bjørner, Bill Shirley's, Sergei Romanenko from Moscow, Netbay Voda, and me in need of a haircut out here on the wing. And tons of other great people, Henk Paren, Dragt, Olivier, and so on. One side effect of this was this kind of excessive recognition that Fritz mentioned, that his advisor came in. So I started I was still a master's student. I hadn't even finished my master's thesis, but I got a lot of mail of this sort to Dr. Sestoft, an invitation to strange things and so on. So that was, of course, great fun. A lot of stuff followed by other people dealing with much more complex languages like full scheme or C, Lars Ole Andersen, Prolog, and the lambda calculus, and tons of other work. Lars Birkedal here in the audience wrote a handwriting codegen approach for standard ML. I think that we were lucky that Lisp is dynamically typed, because types do get in the way here, and Lars and Morten Velinder found a great way around that in their handwriting codegen, and tons of other stuff, not PE related. And then Neil decided in '89 to collect all of this knowledge in a book, and this took only 4 years, and this book is authored by Neil and me and Carsten Gomar, who was doing this lambda mix thing here. And there are also contributed chapters. One of the many things that came out of it, apart from partial evaluation, was that Lars Ole Andersen, to make partial evaluation for C, he needed a way to know which pointers pointed where, especially function pointers. And so he wrote a pointer analysis, which is a super cited paper, and Bjarne Stensgaard later made another implementation of such a pointer analysis using techniques from Fritz's type inference work, and those are super cited papers, both of them. And it's basically because this need for partial evaluation of C was perceived at some point. And finally, we are at PEPM here. after the 0th PEPM, a few years passed, and then Olivier Tanville and Charles Concel decided to create a symposium as a venue, as a permanent home for this kind of work. And they succeeded extremely well. Thank you. Questions, comments?
Corrections? Historical corrections? Lars? No, just...
Neil wrote a very beautiful paper, I think also in the beginning of the 80s, if I'm not wrong, you correct me if I'm wrong, on higher order flow analysis of Lisp expressions, which is a very beautiful paper, I think. Do you know if he was motivated by this stuff when he did that work?
No, I don't think, I think he did it before the partial evaluation work, but that is a really nice paper. But I think it predates this, as the one where he uses grammars to as a semantic basis. I think it's before actually the partial evaluation, or concurrent with that, but it wasn't motivated by, as far as I recall, by applications here.
I just wanted to say that your book, or the Jones Kumar Sestov book, is still one of the two main sources used at DIKU for teaching about partial evaluation, actually.
Thank you. After 30 years, I think that's okay.
So let me be critical here. So partial evaluation was a lot of activity, also with practical tools like for C, for Scheme, of course, or Lisp versions of it. And then it somehow dissipated. Or what happened?
Yes, what happened? I think, first of all, that if you look at self-application, it was super exciting and motivating. Actually, the approach of handwriting, the compiler generator that Lars and others did, and also the people in Sweden actually already in '76 for Lisp, is in many ways, seen from a practical point of view, more useful. It's easier to control, and it's actually not so difficult to, if you have this ability to look at a program and see two different binding times in what's going on, then it's actually not sort of terribly complicated compared to self-application. So I think for practical purposes, a handwriting code gen approach is actually super powerful and useful. And then you can ask, is that actually ever used? I don't know. I think that many people who write program generators then handwrite the single program generator. So instead of handwriting the sort of code gen thing that does the intentional currying of code. I don't know what sort of happened to the rest of it, but the focus on self-application was probably a bit overdone, although super interesting from an intellectual point of view. I think a lot of people actually more or less implicitly use binding time concepts and partial evaluation concepts, and it may be a little regrettable that we maybe somehow missed the opportunity to set terminology and so on in this area, but maybe it's it was there already in many ways. So,
Thanks. Well, then we've seen some presentations also on having two stages. Not self-applicable, being very useful. I mean, for example, the lightweight staging framework by Dirk Rumpf and his colleagues has been used to generate very efficient SQL query processors by basically turning the interpreter of queries by compiling them. Yeah. So
I can say also I personally had a great deal of fun with these modern execution platforms, the Java and .NET platforms, where you can generate bytecode at runtime and get it compiled to machine code at runtime, and you can do some rather amazing things performance-wise using this technology. But the frameworks that have been written for it aren't sort of very concept-friendly. They are you need to do a lot of hacking. But it's fun to do this kind of stuff also. That it might have been nice if those frameworks had been more informed by concepts of binding time, for instance. But maybe that's what GIAC is doing.
Well, thank you again. Don't leave yet, because we have some, it's like with Greeks, we have gifts. So, since I had to bring back some very special native things from Denmark, since you don't, well, okay, you know them. So, here we go. We have to make sure. I hope you don't misinterpret it, because gammeldansk is a traditional Danish undrinkable thing. Sorry, I didn't say that right. It's very bitter. Okay, so but you've really made it sweet now, and of course a PEPM. Yes. Thank you again. Oh, I don't know how to get it on lunch there, but. So, and thanks again, Peter. And next talk is going to be by Alberto Rossi. Please sit up here. Alberto has been working with program transformation more than anybody I know, right? So there's a number of things that stick out in my mind, at least. I early on learned about the tupling transformation. This is Alberto, of course, very associated, authored of, and also the application of program transformation in logic programming, and with your co-authors is defining over many decades, you could say. So thanks for joining us and giving us your perspective on program transformation.
This is the title of my talk, and the paper has been written with the cooperation of Maurizio Proietti, who actually was the first co-author, was involved in this project since the beginning, and then two more, Fabio Fioravanti and Emanuele De Angelis, who developed the implementation of the systems. Yes, thank you. So many thanks to Zina, you, Fritz, some members of this committee. I thank also my colleagues and my students. And this talk is going to present some results on program transformation, both in the area of functional programming and logic programming. It's dedicated to Neil Jones, to Valentin Tuchin, and to Bob Page. I remember when he invited me to NYU to give a little short course, 3 or 4 talks on the area, and it was very near to me. I remember a telephone call I received in Rome from New York, and it was Bob realizing that he was going to die in a few weeks or a few days, and he wanted to share with me some thoughts which I still keep in my heart. So programs should be correct and efficient. This was the idea at the time. I'm talking about 1980s, because it was a programming the small, not programming the large. So one program could have been sorting. How do you write a sorting program? You could say pick up a nice permutation among all the permutations, but this is an exponential program because the number of permutations is exponentially high. So here is where transformation comes into play. You have the specification like a nice, so the sorting program should pick up a permutation which is ordered. And this is the specification. While the program should be maybe bubble sort or heap sort or quick sort. How do you go from the specification to the program? So there are basically two techniques. One is the schema transformation. You mean this schema written in for specification becomes this schema for the program. So you once and for all, and so let us see an example. Once and for all, if you have the specification of the function f as given by these three equations, you know that by a theorem you have proved once and for all offline that this function f can be computed as the value of the variable t of this imperative program. Notice that from a theoretical point of view, you could say this is not a tail recursive program because after the recursive call of f, you have to do something more. So actually, it's not granted that you can do without a stack, theoretically. And so there is a whole dictionary of these transformations. You may go from this specification written in a functional language. This is the specification. And you may get the efficient imperative program. Efficient in this case means no stack is needed. But the number of steps, so to speak, you see n is going down by 2. And so the number of steps is basically the one of the. So let us look at another approach. This is transformational approach done by rules plus strategies. It's in many steps. These many steps can be viewed theoretically as the way of proving the schema equivalence. And this was developed by Rod Barstow and John Darlington. And Darlington did his thesis on program transformation under Rod's supervision. And a few years later, I also a student at Rod. Rod is not in very good health. He's in a house for elderly people. His secretary told me that she would go to visit him for Christmas, but she was not sure whether Rod will remember me or actually if Rod was able to recognize her as his secretary. So, and so this is the famous function in which this technique, program transformation, was applied in the two-plane strategy. What you do, you basically do some unfolding. You expose the behavior of these three lines in functional program by applying this equation from left to right. So you have that phi of n plus 2 can be computed after knowing phi of n plus 1 and phi of n. And you continue this, and you write, or you depict this finite or unlimited or unbounded binary tree. And you discover some subcomputations. So the left sum of phi of n plus 1 is also the right sum of phi of n. So you need to compute phi of n minus 1 only once, and then you send this value back up to. So the idea is that by Barstow and Darlington, this step was called the Eureka step, the invention step, like Archimedes said, the Eureka. And so if you join together two functions, the sharing subcomputation will emerge. And we will see now. So the rules, and you have to invent this definition. This is, how do you invent this definition? So what you actually have some rules at your disposal. You have the rule of unfolding and the rule of introducing definition. And then the rule of folding, we will see the effect of this rule. And then the rule of instantiation. If you have an equation, you can just give an instantiation for the variable which occurs in that equation. And then where abstraction, which actually allows you to compute the expression E as the value of a variable once for all common subexpression E occurring on the right-hand side of the definition of F. So what you do, you invent this definition, and then you instantiate it with the value of n equals 0, which by unfolding gives you fib of 1 and fib of 0, and fib of 1 is 1, and fib of 0 is 0. And g of n plus 1, this is the instantiation for n plus 1, so this becomes n plus 2, and n becomes n plus 1. And then you do unfolding, f plus 2 is f, fib of n plus 2 is fib of n plus 1 plus fib of n. And you keep unchanged the second part of the tuple. And then you do this abstraction. You see u occurs twice. This is the common subcomputation. So you abstract away u and v, giving this pair for you, and then you do the magic final step. This pair is actually g of n. So now you have a linear recursion, g of 0 and g of n in terms of g of n plus 1 in terms of g of n. So what was an exponentially growing 3 now is a linear going line of recursive calls, and you gain. Work has been done on the power of these mechanisms of introducing functions which do not allow a variant of the algebra. If you only know pluses and comma and tupling, you can prove that you cannot be better than that. You cannot create a faster computation for fib. This is a paper by Zhu. And so then you have to link then the original function to this pair. So you see fib of n is the second component. This is a bit strange because you would say I have to compute the fib of n. Why you force me to compute the fib of n plus 1 as well? So tupling forces you to compute the two while you are. So there is an issue here how to link the definition of fib with the definition of g. So this is much better. You pick up the first component of which is the highest value you compute. And then there is another issue in program transformation. How many times you have to unfold in order to discover all the common subcomputation. So this will be solved in the logic case by strategies. You have a strategy which tells you at least unfold twice, because this is has to do with two values. The distance between the body and the head is 2, so at least unfold twice, for example. And you have these strategies. So how to invent strategies? I don't have an answer. We have examples, and we have provided strategies which are going to terminate, and they are going to produce better programs. This is the technology. So too far. I mean, so exponential time, linear time. Can you have lower complexity? Yes, if you change the algebra. If you allow yourself the knowledge of a multiplication and squaring, therefore, then you get down to a logarithmic time. We will go to the Dijkstra challenge. And then if you allow yourself also the exponential, you go to constant time. The fib of n is these two values, these two roots, etc. It's just this exponential. So in one go, you get the value of fib. Obviously, all this can be, and then if you really want to have the C program or the Java program, you like the imperative programming, then you may apply at the end. Once you have a schema flowchart equivalence. So if you have these linear equations, linear recursive equations which are linear, then you get this program which is equivalent. And this is the iterative program for Fibonacci. So no tricks, no difficulties. Every student should understand this because it's just handle, turning the handle, nothing to invent, except the original tupling function. Why I have to invent this definition of G as a tuple of two consecutive values of Fibonacci. And so this is the paper written by Dijkstra, who also died. And the date of this is 1976. He wrote a letter to Rod Barstow, and said, I tried this function, so you are very good in the Fibonacci, try this function. In the proceedings, the paper, I did actually this derivation, and so that can be done. The solution by Dijkstra has to do with the matrices, which basically 2 by 2, so there are 4 values, and so, but we know that you can do with 2 values only. So you can even, I mean, it's a bit of a saving in space. And if you're like, this is the tupling strategy, is the fast, 3 equations, and then applying the schema equivalence. There were people around, I mean, a decade before, which just produces a collection of schema equivalences, Walker and Strong. I never managed to know the first name of these two. One, maybe, I don't remember which, but the other one was also J. Dot. That, I mean, maybe his first name was J. Dot, or whatever, yes. And so you get down to this computation of the FASC function in applicative language. This is it's a parallel assignment. So these 2 values are assigned to these 2 values. And you get a logarithmic time, and a space is a logarithmic space because of the binary expansion of a number. So what I did in my thesis was to, with Rod, he was very humble. No, Alberto, you cannot put me as a first author, but the ideas were all Rod's ideas. I just turned the handle myself. But basically, lifting up to any linear recurrent relation in any semi-ring structure. So you have the 2 operations, plus and times. So also in the Boolean case, this recursive equation can be in any semi-ring abstract algebra, need nothing to do with just plus and times and arithmetics. So, and now we'll go to non-linear recurrence, which is a Tower of Hanoi game. You know the game. And so in order to transfer this disk from peg A to peg B, you transfer recursively n-1 to peg C, and then you do the move, because now it's free. You do the move, and then you put back the n-1 disk from peg C to peg B. You do the unfolding. You put together all these calls of Hanoi, and these are the pegs in the proper order. You know, I have the number of pegs and the number of disks and the pegs and the order. You see, I change the order. A, B, C becomes B, A, C, B, and C, B, A. So you have this change of the order of the, and so you have basically a tower of breadth 3 function calls, and but any cut will do, because it's like a pebble game. You have to put a pebble in the stop node, starting from 3 pebbles on the bottom, and you can go up, filling with the 3 pegs. You see, you have a peg here and a peg here. You can use these 2 to put a peg here, and so you go at the end. You will be able to compute F Hanoi of n+1 disks. So in my thesis at that time, how can I discover the existence of a moving cut? Of a, racing cut. You can the existence of a cut going from the bottom to the top. And the cut should be of finite breadth. And this is the Tower of Hanoi, and this is the schema equivalence, you see, and this is the final standard of Hanoi. If you allow yourself only circular Hanoi, so you cannot prove the three pegs are not in a line, but they are in a circle, and you allow yourself to move a disk from peg A to peg B, but not from peg B to peg A. Not bad. So all these versions can be easily treated with the same trick of so if only these circular moves are allowed, the breadth of a cut will be 6. You see, nothing to invent. It's just you do unfolding, and then you discover the existence of a cut of 6 function calls. In this case, it's 3. Okay, then you ask yourself, this is not actually really very important. What is the 15th move when you have 4 disks or whatever? And this can be done in a similar way. But there are, like the binomial coefficient, if you do the unfolding, the breadth is not constant. And so you really need a stack. And so you cannot do better. If this sequence of increasing cuts, going up, it doesn't exist, you have to use a stack to solve this nonlinear general recursion. From a computational theory point of view, of course, because you can reduce all computation to all recursion to linear recursion because you use the Turing machine technique. You do a turn of an handle will be a recursive call of the Turing machine. Only the tape changes, but the tape is unbounded. The tape you need for the computation is unbounded in general. So now I'll tell you about this another. Tell me when time. Okay, which is the idea, is the inverse of partial evaluation. This may be of some interest for you. So an expression, so when you do folding, you have to see whether an expression up there is an instance of the expression you have now, so that you could fold. So expression can be viewed as a constant and a sub-expression E. In this technique, you view the expression as the result of an application of a function to E. So the context becomes a function. And so you go to a higher order manipulation at this time. Let us see an example of this. So you have this reverse of a list. To reverse a list, you reverse the tail, and then you append at the end the head of the list. And you want to get a tail recursive program for it. So the steps are like this. So you say rev of L is actually rev of L to which you append the empty list. Then you generalize this constant, becomes a variable x, and then you abstract away from this context, from this variable, and you have this function here. And now having this function f, where you also abstract away with respect to L, you get this function f, which is this lambda abstraction. And at this point, rev of L append to A becomes f of L applied to the singleton list A. And magically enough, now f of L has a recursive definition. Sorry, this x should be there. And in this recursive definition, what you gain using also the algebra of the append, that the append function becomes a cons. and so you gain in efficiency. So going to higher order allows you to reduce efficiency, to reduce complexity. So there was this challenge put by Bird, saying you have a tree and you want to produce an analogous tree with the leaves ordered, but you are allowed only one visit of the tree. So in a sense, you have to suspect. So you see, you have two visits of a tree. You collect the leaves, you sort them, and then you replace using the sorted list produced by this sort function, and you put the leaves in the proper order. Try it yourself, you will see that it's a bit complicated, almost impossible. You have to invent another language with suspension, etc. But you can do with lambda. These leaves replace this initial program in which the sorting is done by merge. And this is the final program where this is an application. The function A applied to A2 applied to the argument A2, and these are computed by tupling. And the first component of this tuple is a function, and so and also requires these four values. 3 of them are functions, and 1 is the list. Nothing to think. It's done by just turning under again, looking at the sub-expression, mismatching, and you promote. Okay, so now we go to the. At least you understood a bit about the functional case. Now, what I show you, only 2 things. Maybe this one, which is good. So you are given this the logic program, which tells you when a string is in the language A to the n, B to the n. So in this context-free language. And you ask yourself for a program which tells you when a list is not is in the complement of AN, BN language. Basically, you start from this requirement that this S is a string, and the string is not in the language AN, BN. Notice when you write specification in the functional case, in the functional languages, you will find difficult to express the not specification. Something is not produced by. While in the logical setting, not comes to you as another logical operator as and or. So we do them, at the end, this is the program you get through unfolding, folding, you see the folding, new 5 requires new 5, new 6 requires new 6. Why new 3 is not there? Because it's just, you don't need it. During the transformation, you see you don't need anymore this definition. And so correspond exactly to the counter machine where you count the A's, A start from A1 plus 1. When it becomes, you subtract 1. And when you get exactly to 0, you get into state which is not a final state. You refuse it. I didn't make all these states. Some are final and some are not final. So this is just part of the picture. But they correspond, all the transitions corresponds to these 3, 9 clauses. And this is continuation logic programming. So I will just finish by 2 examples. One, how can you use this technology for proving, for theorem proving, and one for proving properties of any program in any language in which you have the semantics available. So this is a famous Yale shooting problem. You say when there is the event of loading your pistol, and then the event of being alive or being dead, and you want to know that after you load,
your weapon, and then you shoot, and then you are dead. S should be dead. And you want to prove this property of this program, and this can be done by, the property is written in first order language, which, with the quantifier, with the implication. There is a transformation invented by Lloyd and Topor, which uses negation, but basically this program as a model if and only if the property gamma holds. After a few steps of unfolding, definition and folding, you get down to this factor. So, and what is the model for this? It's just a model in which there is the only expression. So say a model is a set of atoms. There is only one atom, which is G, of zero argument. Is the constant G. You see, G has zero argument, while Olds has two arguments. So final how to synthesize. You can do the same for the synthesis of Queen's program. This is the Queen's program. You do unfolding and folding, etc., and you get out of this program, which is the program of solving the Queen's problem. And so this is to verify infinite state sequence systems like the ticket protocol, and you have the specification always globally, always in the future. If you put a request, you have to wait, but in the future, you will going to use that resource. And so starvation, and this is final program. So you have a program for reversing a list, and you put the value 2 at the end. So SNOC is the function which, given a list and a value, puts the value at the end of the list. And so if you start, so let us see the contract for rev. So if the given list is sorted in ascending order, you reverse. The reverse list is sorted in the decreasing order. So this is the contract for SNOC written as a clause. Sorry, for assorted written as a clause, and for SNOC, the similar. If desorted, and then what you add is the smallest, then the list you get is still desorted. So you have clauses 13 and clause 14, which express these two contracts. You put all together, and you transform, and this is the transform. And you have now the Aldarica space model constructor, model checker, which will tell that these clauses are satisfied. So there is a model for these clauses. So there is a model, since the transformation rules preserves. Can I go back? No. Anyway, since the transformation preserves the model, then if these final clauses have a model, so also the initial clauses, so the initial contract for reverse and SNOC have a solution. And so they are all. So this is basically everything, but I cannot go on. Why not? Maybe I would like to show. Okay, I can't. What's happening? I don't know. Anyway, there was a picture of the cap, of the father of the cap you received of 1993. But you will have in the proceedings the picture of the cap, which the partial evaluation for making coffee. You put first water, I don't know, you partially evaluate the cap with water, and then you add some grain coffee, and then you get at the end the coffee. I don't know what is, but it's written on the back of the cap. And you will see the picture on the proceedings. I finished. Thank you for your patience.
Alberto, you got it backwards. Remember, mathematics consists of actually taking coffee and turning into theorems, not taking theorems and turning them into coffee. But so we are in the unfortunate situation that we have actually time for questions because we're having a little bit problem getting any online. So is there questions?
So in this process of turning the handle and then looking for a racing cut, right?
Yes,
In the search of a function that doesn't require a tail recursive function that doesn't require a stack, right? Is there a method of deciding whether or not this rising cut exists, or is it just sort of by hand?
I'm not able to answer this question. When Maurizio came in my life, I exposed him to the transformation of logic programs, and so the rest of my life was in transforming logic programs. But then, yes, there is an issue of when you can avoid the use of the stack in a recursion. I cannot point out to the relevant papers, but if you may be in contact, I could be able to give you. But this is work done in the 80s, after Wolfgang and Stork in the 70s. All this, yes, there are results concerning this. Negative result, this can never be done, and positive results, this can be done, like in termination proofs.
Yes. Okay.
Thank you very much again. Don't leave yet, Alberto, because you have to also get special cup, of course.
This is how we keep this.
and
Sure.
And you have to drink this. It's equally drinkable. It's a Danish specialty. This is Aalborg Aquavit.
Aquavit.
So you have to hopefully enjoy this in the company with Maurizio and all kinds of friends. Thank you very much.
You're most welcome, and thanks for the invitation again to everybody in the committee.
Thank you. And
actually, the Aalborg goes into coffee. That's a very good.
So for the final contributions and final invited talk here, it's my pleasure to introduce Annie Liu. Annie has been a very prolific contributor also to PEPM, but has actually over the last many years, that's the reason's history, developed the field of basically incrementalization of programs. So she's worked very intensively in a number of other areas also on combining, again, programming languages with algorithmic ideas, generating very efficient algorithms, and doing this in a systematic fashion, in particular by systematic incrementalization and transformation and semantics-based methods. Welcome, Annie, for your presentation.
Thank you. Thank you for that first, and thank you for the invitation to speak at this PEPM history celebration. So I have to say I'm speaking on increment computation, but it has a close relationship with partial evaluation in many ways. I have only 20 minutes or something to tell you about incremental computation. If you don't have questions about it at the end, you can ask a lot more about the connections. And in particular, like first mentioned, actually some important this work was published in PEPM. Okay. I have to first apologize, actually. I couldn't be there in person to some issues with travel documents, let's put it that way. As it happens, I'm speaking at Stony Brook University. It's on Long Island, New York. 30 miles east of Manhattan. So let's start. Incremental computation. It studies how to efficiently handle continuously changing input by storing and reusing previously computed results. Okay, so you may see easily that we want the computer programs to handle input from the real world and real-world changes. Okay, but what if I just handle one static data? Well, computer programs process any non-trivial data, or especially large data, by iteration or recursion. So computations must be performed on repeatedly changed state. You probably get an idea that's fundamental for every computer program. So indeed, it is fundamental and ubiquitous. Just think of your favorite graph algorithm program. That is probably including everything essentially non-trivial. And including, of course, because machine learning is popular, in the training of neural network, automatic differentiation is the core of all of this. Okay, so here is actually the outline. There are two parts. The first is an overview of increment computation, 3 categories. And I will say the essence is incrementalization. Okay, and in particular, there's really interesting connections about increment computation and partial evaluation. Okay. And then the second part is about systematic method for informalization. It actually corresponds to differentiation, except you do it in the discrete domain. But also most interesting is optimization, general optimization using informalization. It corresponds to integration by differentiation. At the meta level above all of this, I really want to show that high-level data control and module abstractions are really powerful, and they enable the development of new and better algorithms and drastically optimize the programs with complexity guaranteed. Okay. So this is really building on the shoulders of giants. And I couldn't, of course, list even a small portion of it, but these are people did a lot of pioneer work. I'll mention some of them. And of course, and the students who helped make new explorations and funding support. So here is an overview of incremental computation. And I group everything into 3 categories. In fact, I did this 30 years ago, but this time I spent several weeks reviewing the material, and this was confirmed, okay? So first class is incremental algorithms, and then incremental evaluation framework, and then incremental program derivation method. Okay, so algorithms, well, by the way, in the algorithm community, there are things also called dynamic algorithm, ongoing algorithm, streaming algorithm, sketching algorithm. They all have the same idea. You want to compute some particular function, okay, such as shortest path, and under some kinds of changes, for example, adding, deleting edges. Okay, and you want to do it fast, of course. By using what you computed before, you add and delete some edge. Okay, and of course, in programming languages, we do incremental parsing, incremental attribute evaluation, the more generalized circuit evaluation, constraint solving. Just every problem you solve when input changes, you have to do it. Okay, so these are particular algorithm changes. So if you try to do in general, there are these frameworks. They try to do classes of programs expressed in the framework and handle a class of change. And most basic thing is caching function results. You computed something before, if the function argument didn't change, then you can reuse it. And if there are changes that you have to recompute, you compute those change propagation and various combinations. Okay, and then finally, these are methods trying to derive for each particular problem and each particular kind of change, these incremental algorithms. Okay, and the general methods, tabulation, it's like memorizing caching, but you transform the program to do it. For each program, you do it differently, right? Specialize best for that program. Finite differencing, you will see some of those, and the database view maintenance. So there were just too many. For individual algorithm, actually, the oldest one is probably this, I think it is, tabulating top polynomials by Henry Briggs in the 1600s. And they compute these tables for logarithms. So, right, a polynomial, and if x changes a little bit, what is the new value? And this method was implemented in the difference engine, is credited as the first computer, Babbage's difference engine. And then actually in the first work on exploring the idea of partial evaluation, actually a general form of partial evaluation, you know some information like x squared m3, and you're trying to use it, it's actually called incremental computer, incremental computing, okay, 1964. And then the first one people credit Michi on memo functions, okay, they actually published in Nature in 1968. It's called the memo functions and machine learning. Indeed, they just caching function results, and later in the paper, he talked about it, and interpolations, approximations. Okay? And then for transformation, so many as part of this study, actually, I found what's interesting was that the pioneers of high-level program languages, Lisp started in the 1950s, and that's for first functions, of course. And then Settle is centered around sets. By Jack Schwartz. There's some records says it was started in 1969 because there was a big book of hundreds of pages in 1970. And even John McCarthy and Jack Schwartz actually had the papers on transformations to do essentially tabulation. Okay, both are, I think, informal, let's say, Settle newsletter. This was some notes I found only just a few months ago we were preparing for this. Of course, there are all these other people did extensive research. Okay, indeed, even 1993, a POPL tutorial, especially giving a categorized papillography, it already has 117 references. And now I think it was 8,000 when I looked a few years ago, a few months ago, when searching for incremental computation. Okay, so essence of incrementalization. I just need one concept, which is called incremental programs. Okay, given a program F and operation plus a program F prime is called the incremental version of F under plus if F computes Fx plus 1 efficiently by using Fx. So you really want to compute Fx plus 1. So you introduce new function F prime, using not only x, y, but r, the previous result. Okay, with that, incrementalization just to compute this incremental version given F and plus. And I say this is the essence. Okay, we'll see. So for the three categories. So an explicit incremental program, as you can see, it is just the same equation we had before, except it's a particular F0, a particular plus 0, and particular F prime. And incremental evaluation framework try to be general. So it is an evaluator of incremental evaluator of some evaluator. This evaluator, of course, as you know, takes two arguments, which is the function and the data. Okay, and it handles some input change. So this is the input change. So the incremental version is the incremental evaluator. It's general because it handles functions, in the language the evaluator handles. Okay, but it's also restricted to a particular class of changes that the evaluator handles, not specialized to each particular program. Okay, and finally, the derivation method, of course, as you can see, if F and plus, you want to get them prime. Okay, so how is it related to partial evaluation? Well, partial evaluation, as you were seen already, right? Function, you can think about taking two parts, and then if you take the value for the first parts, you get a specialized function, and that function then takes the remaining arguments and compute the whole thing very efficiently. Okay, and this is so fundamental to compilation, but because the idea to generalize and specialize, it's just fundamental. Okay, so let's see more connections. So this is actually really intuitive, right? Even these two names. In fact, in POPL'23, as I mentioned, there are two tutorials. One exactly titled partial evaluation, and the other one titled incremental computation. And I actually talked about this 2 years ago, right? And the ACM even had them have paper that's called tutorial notes on partial evaluation. This is the categorized bibliography on incremental computation. Actually, I don't think there was ever any tutorial before or even after for many years, even invited talks. But somehow that particular POPL 30 years ago did this. And in fact, interestingly, I mentioned this paper by Lombardi. It was on the general notion of partial evaluation. About at least these functions, you know something about input, you try to evaluate on the fly as much as possible. But the paper is called Incremental Computer, and particular 67 paper is called Incremental Computation. And this time I actually also found the earliest reference on database view maintenance, okay, by Peter Newman, okay, incremental computation, okay, but in the paper, he actually called it partial evaluation. All right, so actually the word I like to use, right, incrementalization is the transformation, and specialization, you really think like the transformation. And of course, the math under here, this is the Kleene-Sassaman theorem, and I mentioned this is differentiation, we'll see more. So the more precise comparison, of course, partial evaluation is intrinsic for language processing. It's just very core, okay? But it can be viewed as a special case incrementalization, where the plus operation is just, you take two parts, you take some arguments, but the first part doesn't change. And the second part is something new. So incremental computation would try to reuse things on X1 as much as possible. That's exactly what partial evaluation does. On the other hand, of course, information is general for computations, optimizations, algorithm derivation, but it can be viewed as a special case of generalized partial evaluation, because that means you take a program, it takes any information, you try to optimize as much as possible. So you can think you take this information, the X is the plus of some previous thing and the new thing, and the F on the previous thing equals some result. Okay, so the generalized partial version is the almighty optimizer. It's really important to explore the special delta here, right? Special plus operation. Okay, so let's look at the second part now, systematic informalization. Okay, so think it takes, this, anyway, I did this for cursor functions and this for my thesis. Here is the key idea. You transform x plus 1 using the result r of x, fx. Okay, and you can already get an idea. This is exactly the whole transformation method was motivated by partial evaluation. You can do transformation, right? Do analysis and transformation. Okay, this is really the most big influence. So this actually has three parts. You use all the results. You simply separate the computation on x from those on y, right? Here, only thing x, y. And use equality, x equals fx. So if you see fx, you just change that to y. And this fx can be, say, written in pairs. You can use parts of it. And fx can compute things with conditions. So you use it under conditions. And now how to use intermediate result like that, Fibonacci. And it's much harder. But here's the simplification. If you transform the program to save all result and all anything compute intermediate result in the result, and then apply P1, and then delete those not needed for compute the original value. And you can do some smart things to only save those. But anyway, the idea is reduce the hard part to P1. And finally, even harder, something not even in the intermediate result. So here, you want to just look at in here. Something was fx, from fx, or intermediate result. There was something on x that wasn't before. That's the candidate observed information. So reduce to P1. And then you just cache all of those and store and use, reduce to P2. Okay, and this was implemented in some powerful system. It's interactive, but later ones, as we see, recursion function is really hard. It's automatic. Okay, so this is the most interesting part. It's really related to differentiation because when we use f prime, the only difference here will have explicit input change. This is saying how change in input is captured exactly. This is exactly how changing output. And of course, there are much more. Okay, quantum chain rules and so on. The most general information is this remains hard, right? Because function has to be continuous for differentiation, but discrete planes are full of holes. But the interesting part is using for optimization. Okay, so if I did have a Fibonacci function, you say after you compute fn, fn, I'll compute n plus 1. And this method, catch and prune, smartly saying, hey, only the previous one is needed. So I have a constant time to compute Fib prime. Would you do it? Okay, so when you add a loop out of it, to do one at a time, add a linear time Fibonacci. Okay, and this was actually a new road told me in 1992 at the start of my thesis proposal. It only took me 3 years to understand what he meant or why it's integration, because I thought differentiation I was doing was the opposite. So the power is huge. And this is one slide summarizing all of it. So actually 3 steps. Optimization is the middle. So first you want to determine a minimum increment to take repeatedly. So for Fibonacci, right, why you do plus 1, why not plus 2, plus 3, plus k or minus k. Okay, and then you do equalization, use previous result or even additional value. And finally, you will need data structure to represent them. Okay, and actually what's powerful, this applies to all different abstractions. Loops array with no abstraction, set is state abstraction, functions the control abstraction, logic rules abstract both data control, and the functions were just hiding both data control and logic abstraction, right? This is like in target programming, database programming, functional programming, logic programming, and overall programming. And then when you have data abstraction, for all of you see you need I2, right? That's synchronization. For data abstraction, you need to apply implement sets. Okay. For control abstraction, you need to iterate short iteration. Okay. And actually, thanks to my former student Tom Rothwell, who invented this name, because they're really fancy names otherwise. Okay, so here are all kinds of examples people are doing. Okay, and in fact, all of these are ours, except that these marked was by Paul Page. These are all new algorithms for improved algorithms, improved complexities, and Paul Page in particular has all these impressive results. Actually, this work, actually a previous sort of worst algorithm, I mean, the proposed problem received the extra award, I think a year before. Anyway, the key idea is all these, oh, by the way, this even leads to some new languages. The key idea is sets and rules, high-level abstractions are really powerful. Okay, if you sophisticated algorithms, see even these are much longer. For recursion, you do dynamic programming, you're just tabling it, and this was, you do everything the same across components. Okay, and finally, this is a review of everything you've seen. Okay, because there's so many categories, the 3 categories really help you focus on the keys and identify informalization as the essence. And the connection with partial evaluation, there's so much. I cannot say all of the influence I had. I used those books and papers as motivation, especially the analysis to be systematic and automatic. Okay, and then the power of this, of course, to optimization, okay, by doing informalization repeatedly. And the whole lesson is high-level abstractions give you all these. Okay, and in fact, the caching part, the iterate, implement, and the work we did on sets and some additional sort of auxiliary optimization were all published in PEPL. Okay, and here is just an overview of current work. Okay, so for objects, once you have objects, you can be concurrent and distributed, and there's really interesting algorithm optimization problems. And of course, for rules and constraints, it turned out that even the semantics was a hard, challenging issue when you have arbitrary negations and quantification. That's what we have been working on. Actually, we have some nice results there. A simple unified semantics. And of course, our bigger interest, and I really want to get back to transformations a lot more, because I've been doing distributed systems and logic constraints and semantics for the last decades, mostly. But it is the informalization that allowed us to do distributed algorithms sort of more effectively at a high level and define the simple unified semantics. Okay. So of course, we want to do more of methods for now these more advanced algorithms and logic. And of course, even more powerful languages, even higher abstractions. Okay, that's all.
Thank you.
Yeah, sorry, this was...
Questions to Annie?
Hi, Annie. This is Sam Lindley here. Thanks for the talk.
Hi.
You talked about this similarities between incremental computation and partial evaluation. Do you have a formal statement that they are exactly the same thing in some sense?
No, they are not. Here is it. Partial evaluation, as at least commonly studied, right? You have 2 parts. One part is known, and the other part could be anything in the new. It's a special case of incrementalization.
So incrementalization is the more general thing.
Yeah, if you consider, if you only gave 2 parts, one part is fixed, the other one can change. But I said, if you have this notion called the generalized partial evaluation, which you take a program, you take arbitrary information about the program, like x greater than 3, right? I don't know, it's a 5 or 6. And then if you can do a perfect job on that, as I said, it's the almighty optimizer, then you can think incrementalization as a special case of that. Because now the information is just fx, right? X is the plus to something, and one of them has value that can be computed, in constant time, we computed before. But by exploring a particular plus, that's what makes it really, really powerful. Okay.
Thanks.
Excellent question.
This was excellent timing, Annie. Thank you very much. And I know it's not as late with you here, but no, wait a minute, you're 6 hours away, so in the right direction. Right, sorry. Yeah, so thank you very much again. And I unfortunately don't have any liquid I can give you via telepathy. Have to do it next time. But as a session chair, I'll just also take the privilege before I get to lose the microphone to maybe express our thanks as a PEPM community to Meng and to Gabi, who've been the co-chairs. And final announcement, since it says something about the future, may I say that? The future of PEPM hopefully is great. So we're all, actually a lot of us working on making something great again. So the proposal now is that for those of you who feel up to it, we'll go to a pub to discuss the future and all other kinds of things about the history of PEPM. And so if you want to do that, please hang around here. We'll just leave right away, okay? Well, thanks.
Thank you for the organization.
Thanks, Annie.